Well, welcome back, everyone. Hope you had a chance to grab some food, a quick break. We got a full afternoon. Just a reminder that all the presentations, the videos of them are going to be available once they're processed. So hopefully this evening or first thing in the morning, you'll get an email with a link to them. So you can watch them again and get some information off them that you might need. Also a reminder that Remtech's about 3 weeks away. Lots of time to register. We still got room. It's a virtual version. We'll try to make it fun. It just won't be as fun as it usually is. So with our first presentation, we have Jennifer Arblaster with Geosyntec down in Vermont. She's going to give us an update from the U.S. perspective on regulatory and research updates. So,
thanks, Joe.
Just turn that over to Jennifer there.
Let me just turn this camera off and share this. Can you see my screen now, Joe?
Yep, just need the presentation mode. Yep.
Perfect. Great.
Looks good,
thanks.
sounds good. Thank you.
Awesome, excellent. Well, thanks everyone. It's a little bit unusual, I think, to be presenting to a faceless crowd, but I appreciate what I hope is a large audience. I guess we're all kind of moving towards this for conferences, so it's good to get used to. My name is Jen Arblaster. I actually am Canadian. I grew up in Ontario, but I've been working and living and working in the US now for the last 8 years as a consultant. And so I am going to provide a bit of an update, fairly high level update on sort of where we are in the US when it comes to PFAS on both sort of the regulatory and research side of things. So today I just want to talk briefly about sort of the EPA action plan updates and what they've done under that scope of work. Focus quite a bit on sort of the state MCL development. That's where most of the movement has been on the regulatory front in America. It's been on the state level when it comes to PFAS. And then I want to talk a little bit about the Department of Defense Research and Development Program. Under their Startup and ESTCP program, they've been doing a lot of really interesting research as it relates to both AFFF in terms of AFFF alternatives, AFFF destruction, and they've been doing a lot of work on ecological risk assessment. And since I am primarily an ecological risk assessor, I wanted to talk a little bit about that as well. So where we are in the States right now, you know, PFAS are considered an emerging contaminant because of the lack of published health data and because of the lack of federal regulation. Right now, we're really just working, you know, off of the lifetime health advisories on the federal level. But a lack of regulation doesn't necessarily mean a lack of action overall. The way CERCLA is set up, federal agencies are currently mandated to act under CERCLA to address PFAS, regardless of the lack of federal standards to apply at this point. And under state programs, we see a lot of investigations at industrial facilities where PFAS are a potential contaminant being led on the state level. And so what we're seeing really, the primary areas we're seeing action in the US is at federal facilities. So for example, DoD installations, and then under state programs at these industrial facilities where they've either been making or using a high volume of PFAS. Overall, you know, I think the general feeling in the States is that the EPA has been exceptionally slow moving on this. The drinking water health advisory levels are now 4 years old, and we haven't seen any movement on those. But they did develop a PFAS action plan in 2019, and that was really sort of their outline of where EPA was planning on focusing their efforts as it relates to PFAS investigations and regulations. So today I just want to talk a little bit about sort of where we are with the PFAS action plan. Back in February, they released a program update, kind of highlighting some of the things that have been done. So really the key action under this PFAS action plan has been that they are moving forward with regulating PFAS and PFOA under both the Safe Drinking Water Act and under CERCLA, CERCLA being the Superfund program. You know, under the Safe Drinking Water Act, what that really means is that they're moving forward towards an MCL for PFAS and PFOA, MCLs are the maximum contaminant levels for drinking water, and they're the regulatory benchmark that has, a heavy stick behind it, so to speak. The path to an MCL is long and slow, and it averages usually about 5 years from being put on that path forward under the Safe Drinking Water Act to actually reaching an MCL. So that they are moving forward with this does not mean that we should expect MCLs in America in the next year or so. This is a long process. It's also a process that really focuses on treatment costs and feasibility alongside health risks. And so what we often see with MCLs is they may not correlate to a lifetime cancer risk level of 10 to the minus 6 like we often expect for risk-based standards. So even when we do see MCLs, it is very possible that they are not going to meet the level of protection that many state agencies are looking for when it comes to PFAS. Under CERCLA, having PFOS and PFOA listed as hazardous substances under CERCLA will really start to give EPA the kind of the stick it needs to enforce cleanup actions under their standardized RIFS, Remedial Investigation and Feasibility Study process. So really, these are kind of the two things that people have been anxiously waiting for. In particular, having them listed under CERCLA would open up the door for a lot of more actions at smaller sites. Other things EPA has been working on and has made progress on include some revised drinking water methods. So they developed EPA Method 533, which is a drinking water method for short chain PFAS specifically. So now combined that with EPA Method 537, which is sort of the standard drinking water PFAS method, you get a more comprehensive suite of PFAS with combining those two methods. Additionally, they've been working on a non-drinking water method under the Solid Waste 846 method program, and that's going to be for groundwater. So the difference really there being the level of sort of other contaminants or dissolved organic carbon in those water samples. And so this method will be more appropriate for groundwater that is not suitable for drinking water. Some other key things that EPA has moved forward on. So they produced interim recommendations for addressing groundwater contaminated with PFOS and PFOA under federal cleanup programs, which is a really long way of saying basically that under that federal agencies in the US, so that primarily relates to, for example, the Department of Defense or Department of Energy, installations like that, they will be moving forward addressing PFAS based on that lifetime health advisory level of 70 nanograms per liter. And that is their threshold for drinking water requiring treatment or a site requiring further action. They've made a couple additional sort of changes to the Toxic Substances Control Act or movement under that act to regulate PFAS. So under the toxic released inventory, they added 172 PFAS to the reporting requirements. So basically that means if you are a user of a longer list of PFAS now, you have a reporting requirement to EPA on a yearly basis. Additionally, they introduced a significant new use rule for surface coatings and carpets containing long chain PFAS, so they will no longer be allowed to be imported into the United States. They've also been moving slowly towards draft aquatic life criteria for PFOA and PFOS. This has been a couple years now in the making from sort of what we've heard in the grapevine, and it's a slow moving process as well. And additionally, the FDA has been doing a little bit of research into PFAS in food products. They released a study that unfortunately indicated that there was a relatively high amount of PFAS in chocolate cake, which is really disappointing to hear. And they're also working with food packaging producers to voluntarily phase out short chain PFAS from food packaging. The other area that the federal programs have been pretty active is the National Toxicology Program. So they've been putting forward a number of studies related to PFAS, including within the last year, focused specifically, so first was a chronic carcinogenesis study for PFOA, and the results of that study indicated clear evidence of carcinogenic activity in male rats and some evidence in female rats. So that sort of moves the needle on assuming PFOA is a likely carcinogen. They also completed some 28-day toxicity studies for mammals on both a combination of short-chain So PFSAs, so the sulfonic acids, and PFCAs, the carboxylic acids. The overall results of that were that, all of these PFAS affected the same organ systems. They affected the liver and thyroid hormones, but the short chains were less potent. So you needed higher concentrations or internal doses of those short chain PFAS to see the same effects as was observed with the long chain PFAS. They've also been putting forward some toxicokinetic studies to understand clearance of short chain PFAS compared to long chain PFAS, and finding that, as sort of expected from other studies in this area, that these tend to be highest accumulating in the liver of organisms. This is along with a few other studies. They're also looking at immunotoxicity and in vitro and in silico studies, but these were the most recent and sort of some of the key results that they're finding through the National Toxicology Program. So I want to talk a little bit now about drinking water standards for PFAS in America. At both the federal and the state level, the focus has really been on addressing PFAS in drinking water. There's a couple of reasons the focus has been so heavily on drinking water. One is that we know that PFAS have a clear source to groundwater, in particular in the use of AFFF. So AFFF, I'm assuming this audience probably is fairly, up to date on what these are, but AFFF is aqueous film-forming foams. They're used as firefighting foams to very quickly put out jet fuel fires or other hydrocarbon fires. They're used pretty extensively at, for example, Air Force bases or fire training areas and things like that. And once in the groundwater, PFAS are highly mobile and highly persistent. So we do see fairly long plumes sometimes, or large plumes resulting from AFFF use or from other PFAS releases. The only, soft regulatory level we have is based on drinking water in those lifetime health advisory levels. So it's an easier way for folks to start focusing on drinking water. But I think one of the major reasons the focus has been on drinking water is that PFAS were included in the EPA's unregulated contaminants monitoring program back in 2015. And what that is it's the EPA program where every 5 years, all large drinking water facilities or providers, along with a random selection of small drinking water providers, are required to monitor for a subset or a list of contaminants that don't have MCLs. And when PFAS were included on that list, there were quite a number of drinking water providers that found detections. This map here shows the UCMR3 results, where blue were zip codes where the drinking water provider had detectable PFAS in their system. And 60 of these drinking water systems had concentrations of PFOS and PFOA above the lifetime health advisory level. So I think when this data came out, it really kind of kicked off a lot of concerns about drinking water quality across the US. And so I love this figure. I'm borrowing it from the ITRC's recent work on PFAS. And this is just a great figure showing sort of where we are on state-based MCLs. Some of these larger numbers, so most of the numbers you're seeing above 0.07, so 0.07 being that lifetime health advisory level from EPA. Some of the larger values in this were developed prior to that being produced as a federal standard. But what we also see is that a lot of the values now are actually coming in lower. So some of these, some of the more recent values that were recently published as MCLs on the state level, even just within the last 4 months, we see New Jersey, New Hampshire, New York, and Michigan all developing MCLs well below the lifetime health advisory level of 0.07. Interestingly, New York also, with their MCLs for PFOS and PFOA, developed an MCL for 1,4-dioxane, which is the first in the country, set at 1 part per billion for that contaminant of emerging concern. Additionally, Wisconsin and Colorado have recently proposed additional standards for a wider selection of PFAS. So we know that this is going to continue. And as folks, as state regulators struggle with having a lifetime health advisory level that isn't a hard, fast, regulatory threshold to apply, they keep moving forward with developing state-based MCLs. Interesting, and along with being highly variable in the concentration, they're highly variable in which PFAS are considered. While federally, they really just look at PFOS and PFOA. The states are combining a number of PFAS often. So both Vermont and Alaska, Connecticut, and Maine all look at the sum of 5 PFAS, but they look at different 5 PFAS depending on which state you're in. Massachusetts is a sum of 6, for example. New Hampshire developed MCLs for PFNA and PFHXS. Minnesota is applying a TEQ-like approach. So it's kind of all over the board at this point right now in terms of which PFAS get regulated and to what level. So obviously there's a huge level of variability in these state-developed MCLs. And as a toxicologist or an ecotoxicologist, you really start to wonder, well, what's driving that? There are some slight differences in the exposure assumptions used to develop these MCLs, but for the most part, the major difference is in the toxicity characterization. So the toxicity characterization for developing an MCL really focuses on a reference dose. So the reference dose being the safe dose to target, and then you calculate backwards if you want an internal dose on a daily basis of X because X is safe, how much drinking water at what concentration relates to that safe dose, to that reference dose. But reference doses are highly variable and they're subject to professional judgment of the toxicologist developing them. So take PFAS, for example. Most of the reference doses for PFAS are based on PFAS specifically, are based on a single seminal study, Lau et al. 2006. The EPA used the blood serum level effect from that study for their lifetime health advisory level. New Jersey picked the same study as the seminal study, but they decided that increased liver weights were the more critical effect. Texas took that same study and then decided that mammary gland development was the most critical effect, whereas EPA in New Jersey had rejected that endpoint based on it being an unknown mechanism. So Texas picked a more sensitive endpoint, but then they developed their RFD using a different metric for doses than the other states did. And then Maine came in and they just took the average effect from 6 different studies and applied it as their reference dose. So really what we're seeing here is a high amount of variability based on the individual organization deciding what is that critical effect and what level are we protecting down to. And ultimately what you end up is a program where your level of drinking water safety varies by your zip code in America. A common theme that we've been seeing in America really is that where the federal agencies have been slow to act, states have been picking up the slack. We see that on the MCL front. We also see that in areas like ecological screening levels, for example. The EPA is slowly moving towards just aquatic life protection guidelines for PFOS and PFOA. California just released a whole suite of ecological screening levels for a variety of receptors. FDA is doing a voluntary phase out of short chain PFAS in food packaging. Multiple states are working towards full bans of PFAS in food packaging. California recently proposed banning PFAS in cosmetics along with some other consumer products, and that's not really even on the table for the federal level at this point. One area where states are focusing heavily on sort of what's being done on the federal level and kind of joining suit with the federal level is on AFFF, as all of them are moving away from AFFFs that contain PFAS. Which leads me to talking a little bit about the Department of Defense. And they've been, keenly interested in AFFF research over the last 5-6 years because they have both high historic use of AFFF at their installations, and they have a high need for AFFF. They're required under military specification to have an AFFF on hand that can put out a fire should a fighter jet crash. They have a requirement to be able to put out that fire and rescue that person with a specific amount of time and needs. And so, for obvious health and safety reasons, this is an important aspect for them. Their current policy only has them using AFFF for emergency response. Historically, they did do a lot of fire training with AFFF, which did result in some groundwater contamination at a variety of installations. Their current mil-spec AFFF, so mil-spec is that military specification that sets the standard for how quickly AFFF can put out a fire and also how long it keeps that fire extinguished to allow for search and rescue. The current military mil-spec AFFF does contain PFAS, but it does not contain PFOS or PFOA above an 800 part per billion PQL, practical quantitation limit. At the moment, no non-PFAS containing AFFF meets military spec. So they are continuing to use PFAS in their AFFF. However, under the National Defense Act, which is the yearly congressional act that basically gets DoD its funding every year, and a few other congressional actions that have really started to force policy changes on DoD. And the biggest one is that they are going to be required to phase out PFAS-based AFFF by 2024. So you can imagine, with about 4 years on the deadline when they received that notification, they went into full overdrive on trying to understand what they could use other than a PFAS-based AFFF. And their main focus place for research and development under the Department of Defense is their CERTIP and ESTCP. So this is the Strategic Environmental Research and Development Program, CERTIP, and the Environmental Security Technology Certification Program, ESTCP. CERTIP is sort of the research arm, and ESTCP is kind of the field testing, product development arm. And this is a joint department of the DoD, Department of Energy, and the EPA. And they have been very heavily focused on PFAS over the last few years, including research and development on sampling analysis methods, understanding fate and transport better, a lot of work on remediation, quite a lot of work on ecotoxicology, which may be surprising, but the DoD is actually the #1 federal steward of threatened and endangered animals in the United States because they have so many large installations and open lands. So they are actually keenly interested in ecology and ecotoxicology. And then obviously because they're needing to move away from PFAS-based AFFF, they've been heavily focused on AFFF alternatives. I wanted to highlight this link because this is available through their website. And it's actually an interactive PDF where you can go through and click on these different projects to find out more information on what their research is. But it really just kind of highlights, that they've been doing a lot of research. Early on in the early 2011, 2015, they had a couple projects focused on groundwater, but that's really expanded to include a lot on analysis, fluorine-free AFFF, and other research-focused areas. So there's 2 areas today that I wanted to talk to y'all about. One is going to be AFFF alternatives and destruction, because I'm thinking with most of you set in Alberta, that might be of interest to many of you. And then lastly, I'm going to talk a little bit about the ecotoxicology research, mostly because that's of interest to me. So AFFF alternatives, CERTIP has been looking at both evaluating PFAS-free AFFF and non-AFFF-based fire suppression options. The PFAS-free AFFFs are getting really close to meeting mil-spec requirements. They meet the reignition criteria right now. So what that means is the fluorine-free foam are able to put out fires and keep them out long enough to allow for search and rescue, which is great progress. They don't yet meet the speed criteria, but they're getting really close. The speed criteria under military specification is that an AFFF needs to put out, I believe it's a 28 square kilometer fire in under 30 seconds. They can do it in 40 with the PFAS-free AFFF. So they're getting really close. They're about 10 seconds off right now. So we're hoping that they are very optimistic towards meeting that 2024 deadline, but they still have a little bit to go. And interestingly, another big area of research for them has been on validating and how we can clean AFFF equipment and validate that it is now PFAS-free. And this sort of came about because there are so many installations for DoD that have AFFF. So for example, not just fire trucks that will go to an emergency scene and put out AFFF, but hangars and other, built structures often have these AFFF systems in place. And if DoD is unable to clean those systems and just replace the AFFF, they're going to have to go ahead and replace all of that equipment too, which you can imagine is a pretty costly endeavor. So part of their research right now has been on how do we clean this type of equipment and validate that it's PFAS-free so that we can manage to not have to fully replace all of the AFFF systems available. Another area they've been particularly interested in is AFFF destruction. Because they have switched from C8, so from those PFOS and PFOA-based AFFFs that were historic, to C6, which are those short chain PFAS-based AFFFs, they've got this stockpile of old AFFF, and they're going to have more stockpile of PFAS-containing AFFF when they switch out to a PFAS-free foam that needs to be dealt with. It needs to be, destroyed in a way that is environmentally safe. And currently, incineration is the only method that seems to be strong enough to break that carbon-fluorine bond in PFAS compounds. But recontamination is a major issue if it's not done correctly with incineration. There was an incinerator in upstate New York called the Norlite incinerator that was incinerating AFFF, I believe as part of a federal program for an installation in that area. It may have been state though. But what they found is that because they were not reaching complete incineration, and as a result, they were potentially releasing PFAS through the air. And now they're being investigated as a source of PFAS to the region around them, as they've started finding elevated concentrations in surface soil downwind of this facility. So, incinerating AFFF needs to be done very carefully and very thoughtfully. There's two avenues where really positive research has come about. The first is plasma-based AFFF incineration. So that's a really high energy approach. And the second is smoldering technology. And this is more of a slightly lower temperature, but a longer time frame to break down those bonds. And I will just shout out my colleague from Geosyntec, Dave Major, in our Guelph, Ontario office, has been a key principal investigator as part of this smoldering technology. So if you have any questions on that, please do feel free to reach out to me because I can always pass you on to him. The last area where they have been doing a lot of research is on ecological risk assessment of PFAS. They've included a lot of ecotoxicology studies on birds, mammals, and reptiles to develop TRBs. But also, and more I think of interest to sort of boots on the ground risk assessors and people working at sites, is guidance to develop current ERA best practices. There were two documents recently put out, Condor et al. And Zudra et al., that I just want to highlight sort of some of the technical elements of and sort of where they can be a benefit to site-specific risk assessments. So Condor et al., we put together a comprehensive and thorough review of scientific literature. So we looked at hundreds of studies and evaluated a number of toxicity criteria and bioaccumulation values, and then came down to sort of what we recommend as best values for modeling PFAS through food webs using empirical bioaccumulation values, toxicity reference values, aquatic life criteria, and protective criteria of plants and soil. They provide sort of an overall view for sort of a framework for ecological risk assessments. And more recently, we're working on sort of a hands-on Excel worksheet that actually allows you to just input your concentrations of PFOS or PFOA in media, and it will help work through those risk assessment calculations. Zodra et al. Did a really similar approach where they worked through sort of a food web model to then back calculate guidelines or risk-based thresholds for a number of commonly evaluated species. And they also developed aquatic life screening levels for a pretty wide selection of PFAS using the EPA's Great Lakes Initiative approach. And so these are great for sort of a screening level ecological risk assessment approach. A lot of this research is ongoing. You can, follow this link to the CERTA and ESTCP PFAS-focused page and find out a lot more about sort of what research is ongoing down here in the States. And with that, I will just thank you for your time, and please feel free to pass on questions to Joe now or reach out to me with questions if you have them.
Thank you, Jennifer. Really appreciate that. If anyone has any questions for Jennifer, please send them in and I will relay them on. Thanks, Jennifer. Jennifer stepped in at the last minute on Friday and over the weekend to do this for us and put together a presentation, so really appreciate it. First question, the Condor et al. Study didn't include 6.2 FTS. Was it due to the lack of tox information?
That was a big part of it, yeah. So the number of PFAS that were looked at there were really focused on the perfluoroalkyl acids. And so that was mainly because that was where we were seeing both the most tox information, but also, the most bioaccumulation information. So values to understand how these compounds move between abiotic media and biotic media.
Great. Any other questions? Okay, so once again, reach out to Jennifer if you have any questions, and I'm sure she'll be happy to help you. Our next presenter, we're going to go all the way to the other coast of the good old United States of America, to David Fleming with the TSR Group, founder and director of the PFAS program there. David, you should see a message on your screen to share your desktop.
I just shared it. I just clicked the button.
Yep.
Can you see it?
Yep, now just share your presentation. We'll be ready to go.
Let me move that here.
Yep, presentation mode. See at the top of your screen there, there's a button that says display settings.
Yes.
Switch that to view, swap presenter view, and you're good to go.
How's
there
that?
we go. Good, sounds good, looks good. Thank you.
You're welcome.
Once again, David, this is David Fleming out in Seattle with TRS Group on new options for treatments of PFAS in soil and water.
Thank you. Hello, everyone. So I'm going to present today our couple of solutions we have created using thermal technology to treat PFAS in soil and the perfluoride system to treat PFAS in water. But first, I wanted to just share briefly who we are. We're a global company now. We started it 20 years ago. We just celebrated our 20th anniversary last September the 5th. I'm one of the founders of the company. We converted our company to an ESAA, employee-owned company, at the end of 2016. We're highly focused on safety using a behavioral safety-based program. We've completed 200 projects worldwide, and these are our core business is doing in situ thermal treatment for the last 20 years for volatiles and semi-volatiles. We have a high percent of repeat business, 80%. We have a very focused and robust research and development department. As you'll see, we've created joint ventures in Europe, China, and Brazil, and we're a financially very strong company. This is a slide that shows you the different heating technologies and their corresponding temperature ranges and contaminants that we treat, starting with the what we call heat enhanced plume attenuation at the top yellow bar there. That's used for remediating compounds using the in situ destruction mechanisms, primarily bioremediation and hydrolysis, but using heat below steaming temperatures to increase the kinetics of those in situ destruction mechanisms. And that can be halogenated alkanes focused, or even energetics that we've recently done for the U.S. Department of Defense. Electrical resistance heating has been our core business for 20 years. You can see that the temperatures that the ERH can get to are slightly above the boiling point of water, and therefore are focused on chlorinated solvents and other volatiles primarily, like fuel hydrocarbons, steam enhanced extraction, similar temperature point. Thermal conduction heating can also be used in that temperature range, but it can also be used to get to higher temperatures that are necessary in order to remediate these more recalcitrant compounds, including PFAS, dioxin, and PCBs. So our thermal conduction heating methods, we call them coil and rod heaters. We patented these designs as well as applications. We've recently been awarded a patent for using our thermal technology to treat PFAS in soil. We use metal alloys with a near constant resistance. You can see the coil heater on the left, that picture there, and the rod heater on the right. The coil is literally a coiled wire that gets heated to very high temperature using electricity, and the rods are a series of rods that go down a borehole or a casing. I'll show you pictures of them here in a minute. They both are low weight and also can provide lower cost. and are capable of getting up to as high as 800 degrees Celsius. Here we're showing our experience on the left of using temperature on this yellow arrow from 100 degrees Celsius up to 500 degrees Celsius to treat these different compounds from TCE all the way up to benzoate pyrene. So that part of the screen or the slide represents the thermal experience that several vendors have in the marketplace of treating those compounds at those different temperature ranges. And so what we're doing now is transferring that knowledge and know-how into treating these PFAS compounds, both short and longer chain PFAS compounds, by boiling them and volatilizing them, not breaking them down, but volatilizing them and then capturing them under vacuum like we have done these other contaminants that you see off to the left of the screen. We did this first in the laboratory, and this is the results of that laboratory experiment that we did recently. And what we're showing in the bar chart on the left is PFAS concentrations in micrograms per kilogram. And this is 10 PFAS compounds that are shown on the table in the right, the left column there. So we heated this on the laboratory bench for 2 weeks at these different temperatures and saw that at 300 degrees C, we got good reduction, but we weren't satisfied with that. So we went up to 350 and 400 degrees C. And you can see on the table on the right, the percent reduction achieved in all three of those temperature targets. And at the 400 degrees C range, we were quite surprised to see that we could remove upwards of 5–9% of the PFAS from the soil. And this study was published in the Remediation Journal in 2019. So that was our first real aha moment that we saw in the laboratory for PFAS in soil using thermal technology. And then we went out to the field and we built a cell, an ex situ cell, to demonstrate that we could use our heating technology, thermal conduction heating technology, to achieve these temperatures necessary to volatilize PFAS. So this was a cell of clean dirt. It was not PFAS contaminated dirt, but it was clean dirt. And you can see the results of it here, temperature degrees C on the left, the y-axis, and on the x-axis, days of heating operations. So draw your attention to around the 7th or 8th day of heating, we get to 100 degrees C, we begin to see a flattening of the curve because we're boiling all the water off to dry out the soil. And then once we boiled the water off after a couple of weeks, we continue to ramp up and get to the temperature to volatilize the PFAS at 400 degrees C in about 80 days. So now what we're doing is working with the Department of Defense through the ESTCP program that was mentioned earlier, as well as the National Defense Center for Energy and Environment, who have funded a couple of research projects for us that we just have contracted actually in the last 2 weeks. One will be an in situ soil demonstration for the U.S. Navy. The other will be an ex situ soil demonstration for the U.S. Air Force to treat PFAS in soil. We're also working with Major Oil to look at treating PFAS in their wastewater, which is another technology I'll talk about here in a minute. We're in the midst of working with the U.S. Army through the Corps of Engineers to develop another ex situ soil treatment project. And we're also working with the Air Force and the Navy to use our water treatment technology that I'll talk about after soil to treat aqueous film forming foams, the AFFF, with PFAS in them, cleaning out equipment, fire trucks and vessels and those type of structures. So now we're ready to go into the field. Our first project is going to be an ex situ cell treatment that'll be at Eielson Air Force Base in Alaska. This will be the first time, I think, that definitely first time we've done it in the field, and I think the first time anybody's actually used the thermal conduction heating technology to treat PFAS in soil on a site. A couple of slides just to show you some conceptual design drawings of how we build these cells or how we plan to build them. In this ex situ cell example here, we'll use soil lifts. So you'll have an insulating bottom on the floor of the cell, and then we'll bring in soil in different lifts, and we'll lay in horizontal heater wells that are shown here in red at the bottom and then recovery wells also in that same layer, same lift, and then add lifts on top. Once it's built, insulate it and cover it. As you'll see, I have a picture of an example one here in a minute. And then you have your vapor recovery manifold there connecting all of your recovery wells. And then with an in-situ solution that we'll be doing for the Navy, of course, we're doing this above the water table in the vadose zone. And our target treatment area is represented by these heater wells that are installed vertically, the red rods. And then you'll have separate vapor recovery, steam and vapor recovery wells with temperature and pressure monitoring points. And then there'll be a vapor cover at the top to mitigate heat loss, keep moisture or rain from coming into it, and control any steam or vapors. Here's a picture of an example ex-situ cell that was built in Asia a few years ago. But we didn't build it. It was another company that did it. In fact, it was Gorm Heron, who's now our chief technology officer, was part of the design of this. He joined our company almost 2 years ago. But he was part of this in a previous project working for a previous company, but the concept is the same. You've got a layer, an insulating layer at the bottom of this pile, and then you bring in your contaminated soil. In this case, it was dioxin contaminated soil, not PFAS, but similar boiling point. And then you laid your, bring in your lift of soil, then you put in your heater wells and just layer them on, at each top of each soil layer. And you can see the heater wells with the gray boxes on this end facing us, with the recovery wells that are all manifolded into the vapor recovery extraction system on the bottom of the picture there. So then this is covered with a kind of a rubber coated type of material to keep heat in, vapors and steam in, and moisture out. And then our heater rods look like this. This is a series of them just laying on the ground, getting ready to be installed at a site that we're doing now in the middle of the US. We have over 150 heater wells that are treating chlorinated solvents at this site, but these are series of dual steel rods that are separated by these white ceramic circular discs, and those circular discs also keep the rod from touching the inside of the casing. And here we're looking at the thermal conduction heating power control unit on the left, much smaller than an electrical resistance heating power control unit, if you've ever seen one of those, but much smaller footprint. And then on the right of this picture are the heater wells that are installed vertically as well as on angle. So you can install these on angle, vertically, or horizontally. And then these heater wells are co-located with vapor recovery wells also. You would angle in this case to get underneath this piece of the structure that's looks like a small building there inside this building, to get up underneath that, the source area of that structure. Here's our conceptual process flow for vapor treatment. So with our vapor treatment approach that we're planning for the Air Force at Eielson Air Force Base, ex situ treatment, we'll be using likely carbon to treat the vapors, but we think that a thermal oxidizer is a better choice when trying to establish a mass balance, using fluorine as the target contaminant to measure, what's coming out in the vapor and what is actually coming out of the stack of the thermal oxidizer. So we're planning to do that for the Army, using the thermal oxidizer to establish a mass balance. But what we're showing here is the air coming in with a blower into the gas-fired thermal oxidizer. We've got a caustic tank here for a quench and scrubber. We've got brine waste, and we continue to blow, dry the air, and then if we need to use GAC carbon for polishing the vapor. Okay, so that's our treatment technology solution for treating PFAS in soil. Now I was going to switch to what we're doing for treating PFAS in water. And we're using a technology that's called the perfluoride process. This was invented in Germany by one of our in situ thermal remediation partners in Europe. Cornelissen is the name of the company. Martin Cornelissen is the founder of the company and this technology. This process is patented in Europe as well as in the United States. And TRS Group is the exclusive licensee to the technology in North America. It's a basic, simple technology that's based on flocculating the PFAS with the perfluoride, creating a particle that's then filtered out of the water. And so what we're showing on the left is a simple process train. As the PFAS contaminated water comes into a tank, the perfluoride is dosed into the tank. That's identified, the dosing rate is identified on a bench study. And then the particle is created through a weak ionic bond. The perfluoride is positively charged, PFAS, most of them negatively charged, so it creates a nice bond that is able to be filtered out. So you use a filter to clean the water after that bond has been created, as shown here. So on the left, you see the tank with a stirrer in it. The contaminated water comes into the tank. There's perfluoride is dosed into the water. You stir it, you create your flock, and then you use a sand filter to filter out the flock. And then that filter is backwashed, and then the resulting residue, backwashed water is it's dewatered, and then the residue, you have a dry filter cake that does need to be disposed of, but at a much smaller quantity than you would normally have used if you were using only GAC or some type of ion exchange resin. And carbon or resin can be used, doesn't have to be, but can be used for polishing the water. And this technique can remove upwards of 90+% of the PFAS from the water, reducing the amount of carbon or resin that's needed dramatically in your treatment train. So here's some pictures on the left of the perfluoride substance. It's a plant-based oleic acid. It's biodegradable, looks like cooking oil. And then in the middle, you've got your jars with stirrers in them on the bench where we're performing bench studies. And then on the far right, you've got your residue that's been filtered out of that water to capture the PFAS particle. Give you an example of what that looks like. So the treatment system itself is really designed initially to reduce the amount of carbon that you're using and to reduce the size of the carbon vessels as well. We believe that this technology is ideal for treating process or municipal industrial wastewater, landfill leachate, firefighting systems, cleaning them out, the AFFF, treating groundwater. It's easy to plug into a pump and treat system. And as you'll see here in a minute, the reason why the wastewater, landfill leachate, and groundwater and firefighting systems is, we believe, a niche market for this technology is because the perfluoride is not interfered with by dissolved organic carbon or dirty water, like oily water, and other constituents that could be in the water, like carbon and ion exchange resin will get interfered with by those different constituents in the water. So I want to show you some examples. So here we're looking at, this is a firefighting water that was treated with the perfluoride system. And by the way, the examples of these projects I'm showing you were performed in Germany. It's yet to be performed in the United States or North America, but we are in the process of doing that right now. So on the left of this graph on the left, we're looking at the composition of the extinguishing water. This is a 1% Mosul AFFF firefighting foam. And on the left of the graph is concentrations in milligrams per liter. And on the right is the legend describing the 7 different compounds or groups of compounds. The first one being 23 different PFAS substances. So you got 2 milligrams per liter in the initial firefighting water of these 23 PFAS compounds. Then moving down the list, you get all the way over to the right where you've got the brown bar, 1,750 milligram per liter of dissolved organic carbon. This was a fire from oil that caught fire that was put out with this AFFF foam. On the right, we're looking at the elimination rate. After adding the perfluoride at a dosing rate of 2 grams per liter. So on the y-axis, we're looking at elimination rate in percent. And again, the same legend on the far right representing these same compounds or groups of compounds. So the first elimination rate is 99.3% for the 23 PFAS substances. And as you move over to the right, 80.5% reduction of these capstones, 78.3% of the adsorbable organically bound fluorine, and then organic bound fluorine. And then take note here, the cationic surfactant, very low percent removal because it's a positively charged surfactant that does not create a good particle with perfluoride being a positively charged molecule. So you're not creating a flock there as good as these others. Whereas on the anionic surfactant, the purple bar, almost 100% removal because it creates a great particle. The negatively charged anion surfactant with the positively charged perfluoride creates a great particle. So you get good filtering and good reduction. And also take note the dissolved organic carbon, very little interaction with the dissolved organic carbon. So not using up your perfluoride when you've got high DOC in your water. Here is a example I wanted to show you. It's a 10-second video if I can play it. What we're looking at is a truck. Whoops. Try that again. A truck in the Cornelison garage where the gentleman on the, whoops. I'll get this down. Bear with me. Here we go. The gentleman at the top of the truck is agitating the truck forward to get the fluoride mixed in the tank and the work and the valves and the hoses in order to get the perfluoride in contact with the remaining PFAS that's inside this truck. And that's an important point because if you don't do this type of cleaning, thorough cleaning, once you bring in your fluorine-free AFFF, you're likely to recontaminate it with remaining PFAS that's in the truck. We're going to demonstrate this for the Air Force coming up here in the next few months through an ESTCP project. In the first step here, you're removing all of the AFFF out of the truck, right? But PFAS is very sticky, so it's going to stick to the inside of the tank, inside of the pumps, the piping network, the hoses, the valves, etc. So it's important then to rinse your inside of the truck and all those different systems with the perfluoride, that's been added to the water. So you're now rinsing with perfluoride and running it through the truck several times to rinse out all that PFAS through those different runs inside the truck. And then once you've captured the water with the PFAS in it, you then conduct your perfluoride addition into that water and create your flock, filter it out, dewater, and have your residue that needs to be disposed of. So this is one technique, at least, that we're looking to bring to the marketplace in North America to help clean out firefighting trucks and other types of vessels, preparing for fluorine-free foams and not recontaminating them. So in one example here, I wanted to show of the results of a recent project where Cornelison used this technique to treat 5 different vehicles, fire truck vehicles, for the German Army in Germany. So in the bar chart up there on the left corner, looking at total PFAS in micrograms per liter, and the 5 different trucks, and your beginning concentrations of total PFAS, the taller bars, and then to the right, your ending concentrations after cleaning the truck with perfluoride. And then the bottom bar chart is showing the elimination rate for each of these 5 different trucks. And so very high, over 99% elimination of the perfluoride in these trucks. So in summary, we are a global company. Our core business has been in situ thermal remediation, but we've developed new technologies for treating PFAS in soil, both ex situ and in situ, that we're going to be validating here in the next year in the US through the Department of Defense. And we've also got a new technology that we're representing in North America that will treat PFAS in water, called the perfluoride system. And a couple of advantages: there's no interference from dissolved organic carbon or other constituents in the water. Perfluoride reduces the adsorption media that you need, like the carbon or the ion exchange, and ultimately, what everybody wants, it saves money. We figure 25 to 30% savings compared to carbon, or even more for ion exchange savings. So with that, if anybody has any questions, I'd love to answer them, or try to.
Thank you, David. Does anyone have any questions for David? Must be a couple. For the German study, how many rinses were required to treat to what detection limit?
3. There were 3 rinses in each of those trucks with the perfluoride substance, and I will have to get back to you on detection limits. There was upwards of 99% reduction. I think we showed the ending concentrations as low as, well, less than a microgram per liter. But I don't know what the detection limit was. I'd have to ask Cornelison about that, but I could get back to you with that.
Okay. Any other questions for David? What is the cost of cleaning one truck with the process?
Well, it depends on how many trucks. If you just do one truck on its own by itself, with no other trucks, we're looking at a higher price point on the order of $30,000 to $50,000. But if you have multiple trucks, we can get that price point down into the lower end of that range, and even perhaps even lower. And it will also depend on whether it's a mobile treatment system or if we build a geographically convenient, more at least temporary, but not a mobile system, but more of a stationary system. We're looking at doing that. High densely populated areas with a lot of firefighting departments, or airports. So there are, you're looking at $20,000 to $50,000 a truck, depending on how many trucks you want to complete.
Okay. If anyone else has any other questions, please reach out to David directly, or you can contact me for his contact info, and I'd be happy to pass it along. Thank you again, David.
Thank you, Joe.
You're welcome. Our next presentation is Deanna Cottrell with Shell. So I'll just set this up. Give me a second. You should have control, Deanna.
Can you see my screen is the real question.
Yes, we can. You just need to put it in presentation mode. And joining Deanna is Paul Westland with Shell as well. They're going to be talking about sulfolane. So I'll turn it over to them, and then we'll be back for questions at the end.
Sure, quick question. Can you see it in presentation mode yet, or is
No.
it the wrong screen?
It's the wrong screen.
It's the wrong screen. Give me a sec here to
Yeah, that's
try
okay.
and make that better.
It's technology. We're all having fun with it.
Deanna, can you hear me as well?
Yeah, we can.
Yep, I can.
Okay, great.
There we go. You got it.
Got it?
Yeah.
Ta-da!
Nope, now it's gone. Nope, now it's back. Okay,
Oh, is it the right screen now?
it's the right screen.
Cool. All right then. Sulfolane, and I know this is an emerging contaminant discussion. People are like, sulfolane, we've been hearing about sulfolane for quite some time. I know. I consider sulfolane the re-emerging contaminant, or the continuously emerging contaminant. It's a contaminant that we've learned bits about over time, starting in the 60s, but we never seem to close the door on it. And so it becomes out of fashion in a way, and then it comes back. And so I'm going to throw it in the emerging contaminant bucket, even though some of you may know quite a bit about it. This presentation, as Joe said, is going to be kind of co-presented by Paul Westland and myself, and we'll try to keep on track for timing, but if we get down a rabbit hole, apologies. Sulfolane is interesting to us anyway. A quick recap on the compound. So on the right-hand side here, I've got two different visualizations of what sulfolane looks like. It's an interesting compound. It has both carbon and it has the two oxygens. Looks like bunny ears. Somebody told me that a long time ago. I've never forgotten it. But why do we use sulfolane? And the reason we use it is a fantastic solvent. It has low volatility, so it doesn't evaporate. You don't lose mass that way. And it doesn't cause any vapor problems or odor problems. People who are working around it rarely even know that they're working around it. It's highly stable, so you don't have to worry about keeping it for too long, having extra stock. All of those things make it a great solvent. It likes aromatics, so Originally, that's what it was designed for, was to pull aromatics out of condensate because you got more money for aromatics. Despite the fact that it's very happy to work in the aromatics and the oil field, it also is fully soluble. In fact, it's miscible in water. That makes it a good solvent for extracting other things. So it works at both ends of the spectrum. It doesn't like to sorb to soil. That's a good thing. So you don't waste it. It also doesn't like to sorb to sediment that's within your pipes, etc. It doesn't like to stay inside of things. It likes to keep moving. And its density is higher than water, so it's fairly easy to separate out from water if you let it stand, which in an industrial operational phase made it quite a happy solvent because they could just let it phase separate on its own, take the water off the top, back to fairly good quality sulfolane. All of those things also, by the way, make it really tricky to work with in the field, but that's a whole nother presentation. Quick review over the application of sulfolane. So in Alberta, and specifically in my role, I spend a lot of time looking at sulfolane that has been used in a proprietary process called sulfonol that is a combination of amines and water that's used to sweeten sour gas. And I think that's where most people have heard about it. It has a lot of other uses without a lot of fanfare, I will say. It's kind of like this unsung hero. It, like I said, it separates aromatic compounds. It's done that for years. Before you had dehyes, it was the go-to, and it still is used in many countries as the primary extraction method. It's used in forestry, it's used in tanning, it's used in treating of fabrics, it's used as a polymer plasticizer. And the most interesting is it's also the whole reason we have lithium batteries, which nobody ever seems to talk about. So sulfolane can be quite positive and has a lot more uses than just oil and gas. We just don't hear about it as much, I don't think, outside of oil and gas. So what were we here to talk about today? I think a few of you, perhaps in our REMTech presentation last year, had heard that in doing research on sulfolane, Paul and myself uncovered that there was a whole lot of industrial articles that talked about sulfolane, and we knew that it had an affinity for aromatics. We didn't really understand how strong that was and some of the reactions that were happening as a result. And so I'm going to transition to Paul for a couple slides here, but essentially we started looking into this with an overarching question that we'll get to, but maybe Paul, you could give a little grounding on exactly what compounds we're talking about and how they bind.
Yeah, thanks, Deanna. I mean, I like to build upon the whole selectivity toward aromatics here, and I think that's kind of a very interesting point, and it basically ties in all this research with this particular research that we've done at Shell. So, like Deanna, you mentioned before, solvent is amazing. Sulfolane is an amazing solvent for light hydrocarbons. This research was focused primarily on BTEX. So previous industrial and research has focused on the extraction ability and affinity towards benzene, toluene, ethylbenzene, and xylenes. And on the graph on the right-hand side, we see that sulfolane has a very strong affinity toward benzene. And this is why it reaches up to about 55% extraction, followed by toluene, which is about 30%. So there's actually quite a large drop there. This is perhaps by that methyl group on that aromatic ring. Ethylbenzene is followed that by a mere 10%, and then you have the xylenes. And so we actually had to put a separate graph because it doesn't even reach 1%. So there's a large variety of different affinities that sulfolane has towards these compounds. Now, I go back to the first slide where it shows that sulfolane doesn't really have a charge. So how does one think that sulfolane may bind to even aromatics in the first place? And this is really through a lot of hydrogen bonds and van der Waals interactions. So I thought this was very interesting. It kind of starts the conversation piece. as if sulfolane is in fact a great solvent for extracting light hydrocarbons and aromatics within natural gas streams, can these same interactions actually occur in water? And that's something that we'll explore further in this presentation. Let's jump to how these interactions may occur and why we believe that there might be an interaction. So there's a lot of interesting pictures here on the slide, and I'll break it down. But basically, we see that there's a higher affinity of sulfolane toward benzene, followed by toluene and xylenes. We just mentioned that before. What this looks like in terms of its electron density is a clustering effect that might occur with the aromatics. And so I'll start off from the top left, and that shows benzene in that row, followed by the different amount of compounds or different amount of benzene or toluene or orthoxylenes. And we see as we increase the number of these aromatics, it forms a cluster around sulfolane itself. And we see the electron density of these interactions actually occur at the sulfolane moiety group, and that is the sulfur and the double oxygen, the ravadiers that Deanna mentioned before. So these clusters are observed in computational dynamics. We do see the extraction ability in the natural gas streams, and we'll be going into if we actually see that in water. We also see that VTEX absorption is characterized by a large volume expansion. So that was actually very interesting to me, as well as an increase in molecular mobility. And again, the reduced density gradient analysis actually confirmed that in those types of interactions. So Deanna, did you want to go into the next slide? Oh, Deanna, can you hear me?
Yeah.
Oh, sorry. Did you want to go to the next slide?
I apologize. I will get to it. For some reason, my computer was not listening to me, nor could you hear me talking, so I must have muted myself successfully.
Sorry.
Well, we've learned that I know how to mute myself, and now unmute. Apologies, folks. So we looked at all this information that was in these industrial journals, and one of the questions that came out for us was, okay, so we see that sulfolane and hydrocarbons like to join with each other. Great. So if we make a compound that's a kind of potentially temporary compound, we don't know, that is this BTEX sulfolane cluster. So as you saw, the benzenes in the slide before, so the benzenes like to cluster around the sulfolane. So the question that was sitting in our mind was, well, if we've got benzene clustered around sulfolane and we put sulfolane into the FID, is it going to show up, or is it going to, are those bonds going to be solid enough to withstand and the extraction process, if any, depending upon which way you go? And is it possible that we're going to see masking of either benzene or sulfolane because the two have now made a third compound? And which I have to admit was kind of frightening when we thought about it. We said, okay, so we're looking for sulfolane and we know we have hydrocarbons. Do we have a problem here where we're either over or underestimating either the BTEX or the sulfolane or both because of their interactions? So what do we do next? Well, it sounded really simple. Just put them together and look at analysis and off we go. The challenge to that was that fundamentally and especially in a commercial lab setting, and we were focused on commercial labs, we could go to a boutique lab and try to figure out novel ways to analyze sulfolane, but that's really not what everyone is doing and not what we're presenting to the regulators. So let's stick to what are we doing in commercial labs. But that also means that we're not using the same routine method for analysis. So it's not like you're running the same machine for both BTEX and sulfolane, and so you can look for both or either. That's not how it worked. which created a little complexity. I think we worked around it, but it created some. There is the impact potentially of water matrix interactions like redox, pH changes, etc. We did the work in a controlled lab setting. So we didn't go out, collect field data and try to manipulate that in the field. We did take various water sources, but we didn't go looking for sulfolane in existing water. We spiked sulfolane and hydrocarbons into the water. Hydrocarbons have different solubilities than sulfolane. So how do we try to figure out what those would be ex situ when we're really just dumping a whole bunch of stuff into the same jar? So we thought about all those and we tried to come up with mitigations for each of them. And here's kind of what we saw. So the first question was, so we have all these other journal articles that say that sulfolane and BTEX interact, and we've got all these conceptual great drawings that Paul has already showed you. Can we actually see it? And so I'll transition back to Paul for the really technical stuff here.
I'm going to try to explain it as best I can. This is something new. This is quite interesting. I think these interactions with sulfolane are, I would even say, untraditional, just because it's not like a cation and anion type of interaction. These are weak, hydrogen bonds, van der Waals interactions. So how do we analyze and evaluate this interaction without actually breaking these bonds in the first place? GC, that's a very powerful analytical method and instrument overall. And we wanted to see whether or not these interactions exist without using GC. We don't really want to break these bonds. So what we actually did is we ran sulfolane in the presence of BTEX using an FTIR. And what we found was this is the whole spectrum, at different wave numbers. But in essence, there's two major areas that we saw that there was some key differences. So on the bottom left-hand side, there's a zoomed up version between the wave number of, let's say, about 2,600 to about 3,000. This is where we see a lot of vibrational energies between the carbons and the hydrogens. And we see that as a part of the sulfolane compound, as well as the hydrocarbons. Now we do see a difference here between just sulfolane and the hydrocarbons. And so there are some interactions that might occur there. But the major interactions actually occur on the wavelengths between 2,400 to about 2,500. And this is really where we believe that the hydrogen bonds exist between the oxygens off the sulfolane moiety group and the hydrocarbons. And this kind of explains the electron density clustering arrangements that we see on the right-hand side with benzene. So this is just an alternative analysis method to really look at these interactions. We wanted to stop there. Obviously we wanted to continue on to what we traditionally use and then the routine methods. So we transitioned over to the GC. Deanna, did you want to take it from here?
Sure. So again, we went back to commercial analysis. And so we did the study two ways to make sure that we covered it off. Study one, okay, so we're going to run BTEX analysis, and then we're going to add sulfolane to it and see if we can still recover BTEX. And then we flipped it on its side and said, okay, the next time is we're going to run sulfolane analysis, then we're going to add BTEX to the sulfolane and see how that affects it, because we couldn't run them together. And hopefully it would all make sense in the end. We didn't actually use, we thought about and tried putting BT, E, and X all together so that we could reduce the number of runs. That was not successful, and so we ended up having to run individual benzene, toluene, and ethylbenzene xylene compounds. Unfortunately, or fortunately, it worked out. Yeah, so the first one was we ran BTEX with and without sulfolane. The red bars are without sulfolane, and the yellow bars are with sulfolane. So on the whole, what did we see? Sulfolane reduced the recovery for all compounds. So when you added sulfolane, there was something that happened that reduced the recovery. It reduced in a predictable way, or at least a consistent way, that as compared to the affinity relationships that had been previously defined by other journal articles. It went pretty much in order, the exact way that we expected it, with, you know, not too much exception. Benzene was first, followed by toluene, then ethylbenzene, so it kind of leveled out. So that's what we saw when we had sulfolane added to standard BTEX, FID BTEX analysis. And then we did the opposite. We said, hey, what if we had sulfolane the other way around? So how much did we get back? Well, BTEX reduced the percent recovery of sulfolane. Interestingly, okay, so benzene showed the highest reduction of sulfolane, which kind of made sense, followed by toluene, followed by ethylbenzene. The xylenes didn't make so much sense. Xylenes, in my mind, shouldn't have been as high as they were based on everything we've seen so far, but not everything is perfect. So where did we land? If you try to compare study 1 and 2, what does it mean? Paul, I'll fall back to you again.
Thanks, Deanna. I think this is, I mean, we're still working it out, right? I think, you know, there's some things like the xylenes you just mentioned, they're a little higher than expected, but in essence, you know, again, I bring it up to your point, Deanna, that BTEX and sulfolane are not analyzed using the same methodology. So that was a challenge we overcame, and we want to see a direct comparison between the two. So one way of looking at it is a percent recovery impact after the addition of either sulfolane or BTEX using both methods. And what we did find is that there are actually notable differences in the reduction of the percent recoveries with BTEX when BTEX is actually present and are analyzed in the same presence of sulfolane. So we did see the notable difference on that. There were actually similar reductions in the percent recovery when showing benzene was actually analyzed in the presence of sulfolane, and vice versa when sulfolane was actually analyzed in the presence of benzene. So I actually thought that was quite interesting. Two different methodologies, similar reductions, but we don't see that same kind of relationship with any other BTEX. And if we go into the next slide. We wanted to kind of showcase again that these are different molecules. They're all aromatics, but they differ just slightly in their structural components. And we believe that maybe the steric hindrance may actually play a factor in these stacking arrangements, just because, again, they're not really that traditional cation-anion interaction. It's more of that stacking arrangement, stacking effects, and based off electron density. So that steric hindrance actually might play a big role in the ability of sulfolane being, interacting with these compounds. And so that might be a lower reduction, or it might be an explanation for the lower reduction of toluene and ethylbenzene in particular.
Agreed. So we knew that previous articles had shown that BTEX and sulfolane interactions exist. They were all industrial, they weren't environmental, and they were all process unit or bench scale, so not really what's going on. So we wanted to look at, when we tried to replicate this using commercial analysis methodologies, can we confirm that there is a BTEX sulfolane interaction? Yeah. Okay, so then what? Well, while we showed you all these graphs that show you that it validates that these exist, they actually don't cause the analytical results to fall outside the acceptable recoveries that you already have from the laboratory data that you get. So it doesn't fall outside of that 95% confidence limit. It falls within the existing percent recoveries that are acceptable. And so what it says is these interactions occur, but the bonding that's happening between these chemicals or these compounds is not strong enough to overcome the analytical methodologies that we're using. So the concern that was voiced initially on our end, which was, are we masking sulfolane or are we masking hydrocarbons because they have this interaction and have created this third molecule? The answer is no, which I will tell you was a great relief internally and up the chain in Shell, because the question wasn't so popular when it looked like it may go the other way. But we certainly saw, and we ran this a number of times, that the interactions don't appear to impact commercial analytical detections. Now, there's some caveats. There's always caveats. And so we do recognize that there are some differences from lab to lab in methodologies, both in the instrument solvent extraction, whether solvents are used for extraction. And we did this on a limited water matrix. We used a very clean, not DI water, we used actual water that we retrieved from a site, but it was clean. And so, you know, depending upon the other components within your water, especially TDS and dissolved metals, other things could be happening that may not look exactly the same as what the outcome from this study was, but we certainly are very encouraged to negate the large possibility there was a problem. We've now got, okay, there's interactions, but the methodologies we're using in our commercial labs can overcome any of those challenges. We are close to on time, or 3 minutes quicker than I thought. That is all we had today. If there were any questions.
Thanks, Deanna. And Paul, are there any questions for them? I'd like to add that there's going to be a series of 4 talks around this topic and a couple others at REMTech next month. So it's another opportunity to get some more information on this subject. Any questions?
Oh, that's nice.
No. Okay, that's
awesome.
That never happens.
Yeah.
It's been a long day so far. Okay.
We'll take it.
Yeah, okay. So we'll take a break until 2:10, and then we'll come back. So once again, you don't have to log off. Just go get a coffee, check your email, and we'll be back right at 2:10. Thank you.
Thanks, Joe.
Thank
You're welcome. Can I test a couple people's presentation? Eggman?
Hey,
Hey, sorry, how do you say your name? Sorry.
Egemen,
Eggman?
Yes.
Aiden?
Aydın.
Okay, I'm just gonna test yours. Just give me 1 second.
Okay.
See a message on your screen?
Yeah, show my screen.
Yep.
Does it work?
Yep, perfect.
Okay.
Good. Jacqueline, we did yours. I know how to do this.
Yeah, we
Heather, do
did
you wanna
mine the
check?
last time.
Yeah,
Sorry, Joe,
yours-
it's Jackie. We did
Yeah, yours-
mine the last time. We should
Yeah,
be
yours
okay.
is fine. Yeah. Heather, do you want to check yours?
Yes, please.
Okay, just 1 second. Watch for a message on your screen.
Okay, and we'll see which screen it's showing.
Your desktop. Looks
Okay.
looks like my desktop.
Rather cluttered, yes.
Yeah.
Okay, so then I go to display settings.
There you go.
Well,
Yep.
that's
Perfect.
good.
Good.
Excellent.
Great.
No, I'm not. I don't exist.
Hi, bud.
Hey, Joe, how we doing, pal?
Good. Just so you know, we're paused so everyone can still hear. We're on coffee break, so that's okay. We're just going to check your system.
Okay. So do you want me to bring up my PowerPoint?
Just a second.
Okay.
You should be able to share it right now.
Okay, just give me a second. I'm going to close my, I'm closing my email so I don't hear any more chimes. because you know what it's like with me, it doesn't stop. So sorry, say again.
You should have a message on your screen that says, there you go, you found it.
Okay, and then go to this, and then I'm just gonna go to this, go to that. Can you see that?
Yeah, all's good, good.
That's pretty simple, yeah.
Okay.
Good.
I'll be back to you in 9 minutes. Did you get your books?
Not yet, but I do know that with all the fires and smoke that Canada Post was suspending a few people delivering because the air was really bad. When I was even running errands for the day, I could feel it in the back of my throat. So the air is clear now, so I think that backlog should clear itself. We'll get it probably any day.
Okay, cool.
All right.
I'll be back to you in about, we're gonna start in about 8 minutes.
Good, man. So all I got to do is just talk when you tell me to, right?
That's it.
Okay, man. Thanks.
We'll pull a string and you can start talking.
Okay, thanks.
Heather, I think your mic's still on as well.
Joe, I'm going to mute myself for now.
Yep, that's fine.
bar to put this away?
Don't worry about it.
Okay.
Yeah, that won't affect me any. Hey, Joe.
Hey, welcome back, everyone. We'll get started with the rest of our talks, the last 4 for the day. Switching over control. Up next is George Ivy, as you probably know, Bud, with Ivy International. Speaking about the unexpected contaminants present at many of the impacted sites and not the ones you're treating. Part 1 of 2. He's hoping one day to do part 2 of 2 if I let him come back. So I'll turn it over to Bud, and Bud, I'll be back with questions afterwards.
All right, sounds good. I'm going to start my timer so I don't go over on this. First, I want to thank Joe and ESAA for organizing this event. I think it's really interesting for a lot of people to hear about some unexpected contaminants that are out there and emerging contaminants, because it's a real concern that we have to contend with. As Joe said, when I first challenged me with putting this together, I've been doing this for 29 years now, and I've encountered a lot of things as I work internationally, so it became a lot of fun. I started generating slides, I'm like, oh my God, I got a lot of content here. I better just do a part 1 of 2. Anyways, we'll see how interesting you guys find this to be. A little bit about me, those that haven't met me or those that have, my background is synthetic organic chemistry. I'll go in the lab and make a lot of interesting molecules and deal with those challenges. I then had the spur to take geotechnical engineering, and then I later got a master's in project management. It gave me a very multidisciplinary view on things. And then over the last 25 plus years of working in the environmental assessment remediation field, again, it's been really cool for me, and it's actually been a great background to see what's working and not working and be questioned with why. And that actually fostered me to develop technology, which I then patented, and been very fortunate to work on over 2,500 projects globally. And as of this year, I can say I've been to 55 countries in the world. As I said earlier, we've got a lot of patents, trademarks, and things like that, and there's more coming. We've even developed a way to put out jet fuel fires with a product that doesn't contain PFAS, but I won't say much more about that until later. I've been very honored been very privileged and honored to receive several environmental awards. And those that don't know, I'm pretty active. I've done Ironman before, and when I'm not doing stuff like that, I'm really keen on getting together with friends and enjoying some good wine. I love cooking. I like hiking, multi-day kayaking, things like that. So yeah, I really enjoy being active. So that's a little more about me on the personal side. Oops, just a second here. So the presentation today is really intended to be a little bit thought-provoking. It's not intended to be exhaustive regarding emerging contaminants, but just a little bit intended to maybe change the way you think about your due diligence when you're doing work. So I'm really going to be presenting today that tip of the iceberg in a multi-part presentation. And what you guys will experience during your entire careers will be the rest that I'm not talking about. And probably more things will come along that we're just not going to present today. But again, hopefully I'll just open the drapes and let you see some things that I've experienced that you might want to consider on some of the projects that you're involved with. For context, one of the things I used to make jokingly say in presentations, who's older, me or the environmental industry? I won't ask that question today because maybe I don't like the answer. But the first Earth Day actually occurred in April of 1970. The US EPA was formed in December of 1970. Australia Environmental Protection Act happened in 1970. Some pretty significant things happened. Not long after that, Environment Canada was formed in 1971. And then the US Clean Water Act came in 72. And then you started seeing from 1970, 71, to year after year after year, all these European, or should we say the Western countries in the world, all stepped up and started forming their environmental agencies. And so loosely put, the environment industry is about 50 years of age. So it's really incredible. So I often will say to people, when you start thinking about what's happened in the last 50 years, I can only think of maybe the IT field or medical fields, which have done as much a body of work as we have. And innovation is really driving what we do. So a lot of the old conventional ways that we did things are not so much being accepted. We're always looking to be innovative. Science is driving things. And I think a lot of good things are happening. So now that we have a bit of a context about where we're at in this field, it's good. And give me a second here. So the question you have to ask yourself when you're dealing with assessment or remediation of contaminated sites, or reclamation for that matter, is your appropriate due diligence. You'll hear some of the lawyers probably they talk about due diligence and whatnot, or due diligence defenses. So, I mean, you can be like an ostrich and put your head in the ground, or you can try to gather as much understanding and knowledge as you can. Fortunately, we work on teams. We tend to mentor a lot of the new people coming into the industry, and we impart our knowledge on them. We work in teams, and things tend to go pretty good. So it's important to do good due diligence to avert any unwanted liability. Happy to be in Canada most of the time doing work, but when I'm in foreign and working environments, liability is a big driver, and things are a little more litigious south of the border than they are here, and it actually changes the way you make decisions. So the intention of this slide is to be a little bit fun. So it's kind of called Eyes Wide Shut, and my intention here is the days of seeing only what we want or expect to see at contaminated sites are vanishing quickly. So really interesting, you take that image off to the right. It's a pencil sketch. It's in excess of 100 years old, and you see a person basically walking across a stone pathway, and maybe somewhere in Europe. But if you look at it differently, you can see the crown of the forehead, some eyes, a nose, and a mouth in there. Kind of interesting, right? Why not? And then we take the second image here. You can see there's a young lady. There's her eyelash, her nose, her chin line, her hair, and there's her hat. However, if you move that differently, maybe that's the eye, that's the nose, there's the mouth, and there's the chin, and it's an elderly lady wearing a veil. Over here to the right, there's a frontal view of a gentleman facing us, okay, gentleman wearing an earring. However, if you change that, whoa, am I looking front or side on? It really does change how we see things. And what I'm trying to say here is that what we obviously see in some sites are obviously driving or pulling us through that assessment or remediation process. But sometimes we have to stand back and say, what if, or is there anything else that we should be considering while we're doing this to, again, make sure we're doing our appropriate due diligence and we're not overlooking anything. So that's the purpose there. This slide is called the source pathway receptor model, and we all know from a toxicological perspective, if there's a contaminant released through air, soil, water, surface water, any of those vectors, and they come in contact with the environment, wildlife, livestock, or ourselves, there's a source pathway receptor model in play, or direct contact pathway. So when you think of anthropogenic sources, what I'm showing here is like, imagine a factory, and that factory may produce air emissions. Well, what's in that air? Maybe it's NO2, SO2, some other particular matter, which can interact with the moisture in the air, maybe forms of acid rain. Inside the building, we have people working. Are they being exposed to occupational health concerns? Are they storing any chemicals in there? Maybe there's asbestos on boilers. A number of things could be happening. Then we have cases not only we may be storing stuff inside the building, but about above ground, below ground storage tanks. And potentially they could leak whatever materials in there. And if they're of a hazardous nature, then we have to be concerned with them. And then these contaminants, if it's the air, can move through the air and potentially deposit down onto the land somewhere or expose individuals. If it's people inside the inside the buildings, maybe they're inhaling something, they're making dermal contact and there's absorption. Or again, the case of underground or above ground storage tanks, which a lot of us are familiar with, we're moving through potentially vapor intrusion into the building where people are at for exposure, or through the soil and then transporting along that. Or if it's a light, like a gasoline or diesel, maybe it's going to float along the water surface and transport. Or if it's a chlorinated solvent or something dense, it may sink and affect its transport mode. In this case, I'm showing an arrow, maybe it's going to go into somebody's waterway. Or which typically happens in a lot of cases is groundwater recharge to streams and rivers, and then they take off pretty quickly. So just that whole idea of source pathway receptor really dictates a lot of what we're concerned with, and concerns about these contaminants moving along pathways impacting receptors that are regulated. So overview on what we're doing, kind of interesting. So it makes us question what we're dealing with, but hopefully through our conceptual site model, we gather most of the things that are relevant to the site and we're going to be okay. But sometimes there's surprises. Anyway, yeah, and then there's anthropogenic sources, but sometimes there's other sources which are not anthropogenic. For example, arsenic in water in places like New Brunswick or other places. Acid mine drainage, I'm thinking of some issues that have happened at some sites where it's just naturally occurring. Or bacteria or algae blooms naturally occurring, and even from things that are not caused by us. So it's not always what the anthropogenic or man-made sources are. Sometimes there's natural occurring ones that we have to factor into what we're doing. Moving on a little bit here. So imagine we submit a sample to a lab, and we're going to say to the lab, how you doing? You guys are great at what you're doing. Can you do a test for me and determine how many Abraham Lincolns there are per photo here? So this amazing lab does the test for you, gets the PPI, the parts per image, okay, in both samples. So the first one, sample one, they're both supposed to be identical, at least they seem to be from our perspective. We analyze it, hey, there's one Abraham Lincoln per photo. Great, this looks awesome. And then the next sample comes back with the same result, one Abraham Lincoln per photo. This is amazing. However, we know there's a big difference between the two, but on the surface, the lab may not be able to tell you that. So, I'll be bringing up some of those type of issues. In this case, I'm kind of jokingly showing Abraham Lincoln with an AK-47 or some kind of a rifle sitting on top of a grizzly bear. Quite a daunting image, as it were. But I mean, at the end of the day, how many Abraham Lincolns are there per photo? One in both cases, and that's the correct answer in both cases. But there's a difference between the two. So just something we got to keep in mind. You only get what you ask for. If I go and get my blood tested for cholesterol, that doesn't tell me that I'm cancer free. It doesn't tell me many other things. It only tells me what I'm analyzing for, which is the case on what we ask the labs for. So just keep that in mind, right? So no worries. So now what I'm going to try to do is bring up some things that I've had fun with, and often when I'm would teach these courses on phase 1 or phase 2, I talk about a lupo, and I would use a bit of a Spanish accent. And it's not a Spanish or Italian Latin word. What it actually stands for when you're dealing with residential, commercial, or industrial property, it stands for something that relates to a lot of the buildings built before 1980 and sometimes after: asbestos, lead, urea formaldehyde, PCBs, ozone depleting substances. Those aren't the only things you have to be concerned with, but if you're dealing with these sites, you shall consider these, or you should, as potential source of concern. And not only during the phase 1 assessment as potential concerns as your due diligence for your client, but imagine you're demolishing a property and there's maybe some lead on there, maybe there's some PCBs in some of the materials, or there's some asbestos piping. These are things you'll have to factor in because there's even occupational health concerns that you've got to be mindful of. And there's some companies that we deal with in our industry, not only are they dealing with, phase 1, phase 2, phase 3, they're doing asbestos abatement, demolitions, a lot of different things. So these things do pop up. So don't cover up one of your eyes, gotta keep them both wide open. Okay, so here's a good one I like to do. When we're dealing with service stations, the first thing that pops to my mind, obviously, is going to be potential for gasoline or diesel spills, or maybe some of the products they're using in the back maintenance yard on the site, okay? So well and good, that's no problem. We have lots of ability for doing that. So let's say during the phase 2 assessment, you're doing that and you're testing for petroleum hydrocarbons, which we do through F1, F4 methods, or even the methods, whether it's Alberta, BC, or elsewhere. We can capture that quite well. And what we often do as a good screening is we do a total metals atomic absorption analysis, or just total metal analysis. And we do that, you might actually see the presence of lead. Well, you're probably going to compare that number to what the regulator number is, and you're pretty happy with that. No one typically goes beyond that, which is fine. But that doesn't really tell you whether it's a simple Abraham Lincoln or something else. So it doesn't tell you the type of lead you're dealing with. Okay, so in many cases on these older petroleum sites that are actually pre-1990, and yes, there was some leaded fuel around that. There is still some being used in even race car tracks and things like that. And every single jet in the air is using these compounds in their fuel. They're leaded. Yeah, I won't get into why. Anyways, the lead that you're actually dealing with is that anti-knocking additive, and it's actually called tetraethyl lead. It's an organometallic. If you don't ask the lab to actually specifically look for this, and you're doing a total metal analysis, all they're going to do is tell you you have that metal. Just like if you had chromium, well, what forms of chromium in? If you want to talk to Erin Brockovich, she'll tell you it's really important if you know the form it's in. Okay, so interesting. So here's a nice image of it. This is tetraethyl lead, the compound itself. There's 3 ethyl groups around the lead. It's actually a colorless, oily liquid. It's kind of sweet, musty odor. And then you have lead. It's kind of this kind of a blush. It's kind of silver, but kind of dull. It's very malleable. You could cut it with a knife. You could press it. It's used in a lot of bendable metals because of its malleability. It serves a lot of good things. But their two are very, very different. And again, if these are released to the environment, what's the inherent toxicity of the two? We know that lead and paint, things like this, if they get exposed to our children, it's not good for them, causes a lot of issues, won't get into it. But tetraethyl lead has a whole host of other issues associated, which are toxicological and of concern. So you can't say that one lead in one sample and one lead in another sample are exactly the same when they may in fact be quite different. So if the lead number you're seeing is well within the regulatory guidelines and the numbers aren't much of a concern, you're probably okay. However, if it is there, it can affect the way you assess its toxicological impact and also how you remove it. Maybe you're going to do something as simple as excavate out the material to get rid of it. Or there are actually ways of actually liberating and removing that lead mass from the soil so the total metal concentration goes down. But if you're trying to take that lead and you're trying to change it into a form that doesn't dissolve, maybe you have to change it into some kind of an insoluble salt form so that from a leachability perspective, from a source to a pathway, it's not moving, so you've reduced the risk. And that can become particularly important depending upon what project you're dealing with. So you want to be careful about how you look at the contaminants that are present, what form they're in, because it drastically changes the remediation method you're going to apply and the success of that. And assumptions will tend to nip you in the backside. So here's another fun scenario that I've actually been involved with more in the United States than Canada. I could say that in the middle of August, suffering from my lack of travel, I actually went across Canada between Vancouver and Montreal on my motorcycle. And I really loved my trip through southern Saskatchewan, seeing all these grain elevators. It was wonderful. Anyways, aside from that nostalgic aspect, something you need to deal with, you're dealing with these grain elevators, for them to store fuel or heating fuels for operation of those facilities is not uncommon, okay? What we're not often aware of is, or we overlook, is the fact that we use fumigants, which were applied to the grain to preserve it and stop insect infestations. So that we could preserve it so it can actually get to port, which you're seeing here in the middle photo. And these older sites sometimes are then demolished and redeveloped. So if you're looking for typically the fuels that were stored above ground, below ground, the typical suspects, you may overlook the fact that there's actually fumigants used. And just by case of example, in the United States, 2.7 million kilograms or 28 million pounds of fumigants were used nationally in 1978 alone. So in working on sites in the United States, do we look for this every single time? Or if the client's not aware of it, we bring it to their attention, liability will basically force their hand to go look and make sure if it's present or absent. So in those cases, you're looking for carbon tetrachloride, and we know carbon tetrachloride is carcinogenic and it's quite harmful, and there's carbon disulfide. So yeah, if you overlook that, it could have some significant consequence for your site. And jokingly about what we see and we don't see, it's your due diligence. But funnily enough, when they were destroying this grain elevator, in the foreground of that photo, there's a dog. He's hunched over, the hair is raised in the back of his head, his tail's out straight. He's ready to take on this grain elevator, it looks like. But yeah, it's funny. Another scenario we often get involved with is chlorinated solvents. Nothing surprising there. We've been using for a long time for dry cleaning operations and facilities. So you're dealing with the, perchloroethylene, trichloroethylene, cis and trans DCE, and vinyl chloride. These are all sources of vapor intrusion, soil and groundwater contamination, and they have, as we know, human ecological toxicity at very low parts per billion concentrations. That in of itself is not the purpose of the slide. What the slide purpose is that there are chemical additives, and me from an organic chemistry background, I'm very aware of that. There's a lot of chemicals that are made and we add these stabilizers to them. In the case of these compounds that I've mentioned, it's not uncommon to add 1,4-dioxane to them to stabilize them, and a lot of ways to keep them from breaking down and make sure they last longer in storage, just like preservatives and things, so that they're available for use at the dry cleaner with good performance. Unfortunately, if you're cleaning up one of these sites and you decide to overlook the fact that you might have 1,4-dioxane in the soil or groundwater, you may be missing a responsibility to check for that. And unfortunately, 1,4-dioxane is a very low soil and groundwater cleanup requirement. The other thing you need to be mindful of, although we're dealing with chlorinated halogenic compounds on here, it's not uncommon sometimes to see brominated forms of those compounds. So if you don't ask the lab for it, eyes wide shut, you won't hear it. If you ask them, you might be surprised what you can find is at the site. And then of course, our clients will try to influence us to do the right thing, and which we try to do. And sometimes we can overlook these things, but it's nice to be mindful that they might be there. And if they are, it may require you to send at least a limited number of samples in just to do your due diligence to ensure their absence at that site. Particularly if your client's looking to buy that site, the last thing you want to do is have them buying a liability. And just for fun here, since it's with ESAA, I just looked up the soil limits for 1,4-dioxane, and these are 0.00025 milligrams per kilogram. Basically, you're talking parts per billion in the soils, just to say that you're not allowed very much of this material. And unfortunately, because of its electronegative characteristics, it absorbs to the soils, but also has a solubility, so it creates a lot of concerns, and you just have to be very, very careful. But in addition to that, when you're dealing with these sites, there's carbon tetrachloride, you can find free on some of these sites. You can find Stoddard solvents, because they were often sometimes using these to help bring stains out of things. Kerosene was actually often used at these, and certain types of mineral spirits. So when you're on some of these sites, there's a typical suspect you're looking for, but sometimes you have to perform other broader scans to see what other forms, you know, Abraham Lincoln might be in that could be a concern. That's kind of interesting. Now, because I'm a chemist, I like to bring up chemical things. And one of my favorite things to show up is A plus B producing 100% of C. Do you know there's next to maybe 1 in 100,000 reactions can actually make that claim at 99.9%. The reality is these reactions always produce a certain degree of byproducts or unwanted things. Sure, we look in our textbooks and we see A plus B doing a certain type of reaction produces C because we really are interested in C. Maybe it's vitamin C, maybe it's a cure to cancer, maybe it's something to get rid of my headache. You know, we're obviously interested in that, so those reactions and how it's done is important. And then you purify to isolate C away from D, E, F, G, H, I, whatever else might be in there. And if you actually went back to the reference materials, you'll actually find in those what is the yield on those reactions. You'll never find 100%, which means that there's other stuff being formed. And organic chemists, we can often predict what those are, and that's why all reactions go through a purification process afterwards so that we can isolate what you guys want. So if you're doing kind of chemical oxidation, reduction, and there's other forms of reactions which we don't talk about, you're often producing byproducts. Sometimes they're really of no concern. But in other cases, you may actually be forming Abraham Lincoln with an AK-47 on his head. Or if you have if let's say we're analyzing for an Abraham Lincoln with a top hat holding an AK-47, and then somebody knocks his top hat off, next time you analyze it, he'll come back negative because he's missing the top hat, but he's still standing there a little bit disgruntled because his hat's knocked off, holding that AK-47. So just be mindful. You got some clever people at the lab, and they can see a lot of things if you ask them to. Yeah, kind of neat, eh? And as I said, a lot of times in industry, we deal with industrial, commercial, agricultural, medical, research grades. And of course, when you're dealing with industrial commercial, that's the least expensive. As we get into agricultural stuff, because exposure to people, medical, research grades, the cost goes up, but the purity goes up significantly. Yeah, the cost per liter or something for industrial commercial applications is peanuts compared to the same 1 liter volume for research grade. It might set you back in your seat. Yeah. So there's also things to keep in mind that when we're dealing with degradation byproducts, you know, we're talking about chemical reactions, but even bacteria, when they're breaking things down or altering, sometimes they even create intermediates from your starting compound through the degradation process, which sometimes go up, not down in toxicity. So that's something to be mindful of. So pollution with perchloroethylene or PCE, if you see PCE, look for its toxic buddies, as I like to say. So if you have one, you'll often deal with TCE, which is a degradation product of PCE. If you have cis or trans DCE, in this case, if you have cis, which is a degradation product of PC and DCE, oh, you see the interrelationships there, right? Anaerobic dehalogenation of TCE. And then the list goes on. Here, if you have the trans, it's buddy for DCE, is a degradation, also a degradation product of TC and DC. If someone ever wants to know why you have a cis and trans, call me up, I'll explain to you, it's really easy. And then we have that bad little boy called vinyl chloride that's out there. So if you see one, look for its buddies, do not assume it's alone. And as I've shown in the upper right here, if you tend to have some of these guys around, it's not a bad idea to send a few samples in and check them for dioxane. You might be surprised what you see. Something else is when you start looking at thermodynamics, first law of thermodynamics says you can't make or destroy energy or things. So if you're doing chemical oxidation or reduction on site, whatever you're using and introducing gets introduced. It's there. It may result in the breakdown of those contaminants of concern for you, but if in this case we're dealing with sodium permanganate, you're introducing magnesium and sodium. I've actually been involved in projects where the EC and SAR levels post remediation, and it was successful, are through the roof at a concerning regulatory level. So keep that in mind, that you might cause issues. So you might want to figure out what your baseline conditions are before. And in some cases, you can easily remove these. In other cases, it may not be. And something else that happens with chemical oxidants, we know that oxidizers tend to rust metals. Well, they interact with the geology, and they actually may close off or cause crusting, as some people use in terms I see at conferences, and close off pathways. So keep that in mind when you're looking at things. And as our field advances, we'll be evaluating the consequence of that more and more and more. So there's sodium, there's potassium permanganate. So you might want to look at some of these and see what they're like, right? And sometimes it's not very expensive to do that in a metal analysis. And if you see concern levels, that's where you probably want to look and see what form that's in, and to see if you have any concerns on your site. And I know EC and SAR can be a concern in Alberta and BC. Now, the next thing I talk about is, again, that whole idea of doing in situ chemical oxidation, in situ chemical reduction. These are significant reactions. And I told you before, there's no A plus B producing 100% of C. So there's certain types of byproducts. In some cases, these byproducts are really not much of a concern, nothing to be really worried about. And the lab can actually identify them if you're so inclined to do so. And the very first time I ever did it in my career was actually back in 1989, where we actually were bioremediating some soils at 40,000 parts per million. And over a period of time, it went down to 10,000. I actually got the lab to take some of, like, their, should we say, their wash or workup water, analyze it, and I found the other 30,000 because they were basically oxygenated alternative forms of those petroleum hydrocarbons being sequentially degraded. A really good story, but at the time, people didn't have much of an appetite to learn that. They were just happy it went from 40,000 to 10,000 on its way to cleaning up the sites. So again, your due diligence, what do you want to see? Do you just want to say, oh, there's one Abraham Lincoln per sample, or you maybe want to check out what form it's in? So again, I just want to challenge the way we sometimes think of things, right? The other thing you have to think about too is sometimes you have like a phenol. Well, a phenol under certain pH conditions has a certain toxicity, no question about it. But if you alter the pH, you can actually increase its associated toxicity, its solubility, and its ability to interact with other things. As a consequence of that, it can become a problem. Source pathway receptor, phenol has a solubility of 84.2 grams per liter. Well, phenoxide has a 98% solubility, even better than ethanol in water. Imagine that. So as far as getting in water and moving, it could be a concern. But just keep these things in mind, that pHs do adjust at sites, and that may actually change the way we look at our source, our pathway, and the potential risk to receptors. Again, this is a bit heady in some fronts, and maybe beyond some of the ways we look at things from risk perspectives, but I think it's worth thinking about as we advance our science. I'm going to probably get really close to cutting off on my first part. Even the chlorination of drinking water, we all know that before they did it, cholera, typhoid fever, dysentery, which is still a massive issue globally. You would not believe how many people are dying from it still. Hepatitis A killed thousands of residents annually in the United States. They kept great records of this. And there's just a nice plot, just giving you an idea from typhoid fever, the reductions because they chlorinated water. It's been really, really, really good for us. However, when we're dealing with it, we do this disinfection, there are byproducts. Sorry, guys, that's what happens. And they call them disinfection byproducts, and they happen. Even when somebody's ever worked at a lab and you guys were decontaminating your lines and all that stuff, you use this kind of an iodine compound, you form them too. So there's contaminants called trihalomethanes. And if you look at the type of potential issues for liver, kidney, central nervous system damage, there's halo acid compounds, bromates, chlorites, they're concerns. Now, if we look over here where I've kind of circled over here the limits for removing certain types of bacteria of concern or viruses, the LAWA limit is approaching 0. They don't want anything in there. So of course we want to get rid of that. We just have to be mindful that we might form byproducts in our water disinfection. Maybe that's why some people like their Brita filters and other things to extra purify our water at things. I'm getting really close again to writing this down. All I'm showing here, here's a whole list of metals and their counterparts, okay? And depending upon the form that metal's in will change whether it's going to be insoluble, a little bit soluble, or very soluble from the source pathway receptor. If it doesn't move, it's not going anywhere. The dog's been leashed off. But if the dog's not leashed off and he's in a cranky mood, he might go bite somebody. So you got to be mindful of the fact that there's different forms. And depending on the different forms will affect how well it moves. And I've identified things like bromium, which is a concern. Chromium, we know Aaron Brockovich is concerned about that. Lead, and then mercury. in its various forms. So just something to be careful with. And to look at things like TCLP in the United States, if it doesn't leach, it's not going to be much of a risk. If it does leach, then it's a big concern. So just keep that in mind, right? The last thing I'm going to probably say before I get into my last couple of slides is we know there's concerns of PFAS. You heard about it today. There's these long chains which have gained tremendous amounts of concern in firefighting foams and everything else that's being used in. And a lot of people are now thinking about changing that to the short chain because there's less known about them. I'm here as an organic chemist to tell you these guys are as bad, if not worse. Big warning. And they are being banned globally. South Australia is all over it, Europe's all over it, and I know we're taking on PFAS, having a struggle with it. You just want to be careful of changing long to short. It's a bit of a concern, right? So I suggest you not to do that. So in this one here, I'm kind of doing my time check because I'm pretty much running out of time. I have a whole host of other slides that in some cases like lead and lipstick, a whole bunch of other things that people don't know about, spraying oil on old dirt roads. The list goes on, but I'll deal with that another day. So that's my buzzer going off. So I'll stop at that point, and there's my contact information. And I thank you for the time that you give me to do this.
Thanks, Bud. We'll have to have you back to do a whole day, a whole hour on your slides with your energy there. Does anyone have any questions for Bud?
So, Joe, I can't hear anything right now, so just give me a second.
Are there any questions for Bud?
I can hear now.
Yeah. I was saying, Bud, that we'll have to have you back just to do a webinar with your energy just on this whole topic. I have no questions. You can reach out to Bud, and then he'll be happy to get back to you. We'll move on to our next presentation. Thanks again, Bud.
No worries. Thank you.
Okay, our next presenter, Egwin Eiden from the senior chemist from Agate Labs, is up next with his presentation. You should have control.
Okay,
Sure.
can you see my screen?
Yep, we're good. Looks good.
Hello?
Yep, looks good.
Okay. First of all, thank you very much, Joe and ESAA, for this opportunity for presenting our study. And it is related with contaminated site and named after contaminated site and landfill origins of PFAS and determination of leaching characteristics. So I know we talked a lot about types and sources of PFAS, but let's talk a little bit more. We listened a bunch of talks about PFOS and PFOA today, and there's a big attention about that. Even though they are not used anymore, they are still in the environment, so we have to keep attention while we are widening our attention because there are more compounds there. So we need to increase our focus instead of changing our focus from PFOS and PFOA. So we are trying to do that here. We want to keep PFOS and PFOA and increase the number of compounds we would like to focus. And all of those compounds are coming from different sources. Since we are dealing with landfills and contaminated sites right now, landfills is full of like fast food packaging and non-stick cookware. And contaminated sites are mainly contaminated with firefighting foams, and we can say mostly airports or military bases are a big concern. When we talk about transport of the PFAS, actually, can I? Okay. So our focus, as I said, firefighting foams, AFFs, and they are when they are used, they contaminate this land. And we want to learn how the PFAS in AFFs leach to the groundwater, or when this contaminated site is remediated via land dumping that contaminated soil to landfill, how it affects leachate of the landfill. So contaminated soils, how it happens, so the AFFF is used, and it can come from the leaks or spills from the concentrate foam, or when it is used, it can cover the soil, and with the surface runoff, the PFAS may go to water or sewer system, or it may infiltrate to groundwater. So since there is limited remediation options for contaminated soil, we focused on landfills, and there are a lot of applications about sending the contaminated soils to landfills. So our concern is that. And yes, there are lots of good research about PFAS transport, but still there's a lot of different types of PFAS coming, and all of them have different properties. And still, I think we have limited understanding for PFAS transport. And different PFAS have different behavior under different conditions. And this also applies to leaching characteristics, and soil type dictate that leaching characteristic, and the PFAS properties also have a role on it. And we have limited data available on leachability, and there is a lack of any soil acceptance criteria for PFAS disposal to landfills. There is Ontario regulation, which has roughly 100 times Ontario drinking water standards for some compounds as leachate criteria, but it doesn't include PFAS. So the problems are limited PFAS remediation options for contaminated soils. There is no regulatory criteria regulating sending of PFAS contaminated soils to landfills. And there is a big lack of understanding of leachability, which may lead to possible contamination of groundwater or possible contamination of surface water. And our objectives, that we have 3 objectives in the study. First, to identify leaching characteristics of PFAS in soil in relationship with soil type and PFAS type. Second, to determine potential impact of contaminated soils to landfill leachate, groundwater, and drinking water. We also want to generate data which can be used to develop a predictive tool to determine if contaminated soils can be sent to landfills. So we designed several experiments to achieve these objectives. And first experimental design is we spiked the sandy loam at different concentrations of AFFF without PFAS or P4A. It is currently used AFFF, and we characterize that AFFF. We characterize the PFAS in this AFFF. And after spiking, we homogenized the soil and took samples for PFAS analysis in soil, and then applied TCLP procedure. And we measured PFAS in leachate, and we also did top assay in the leachate, and we measured the PFAS after top. And on the second phase, this time we changed the AFFF. We used the legacy AFFF with PFAS and P4A, and we used different soil types, again, different concentrations, and similar scheme of experiments. We homogenized the soil, sampled and measured the PFAS concentration in soil, and we did top assay in soil as well. And we applied TCLP test, and measured the PFAS concentrations in leachate, and we also did top assay to leachate and measured PFAS concentrations after top assay. So for measurement, we have measurement of PFAS. We have in-house developed PFAS method, which complies with EPA 533 method. In summary, for soil samples, we extract PFAS with sonication and dilute the extracts, and that extracts go through the same procedure with liquid samples. And liquid samples, we adjust the pH and extract with salt phase extraction with water oasis wax cartridges, and then measure the PFAS with Agilent 6470 LC-MS. This is a sample chromatograph that we have, and we measure 45 compounds. We quantify 45 compounds, which is much more than listed in any EPA method 533 or 537. Our detection limits are in range of 1 to 5 nanogram per liter for water samples, and 1 to 2 microgram per kilogram for soil samples. So when we are dealing with TCLP, we wanted to define something as to measure how the PFAS leaches to the water phase from the soil. So we defined the term called leachability. So when we think about the TCLP procedure, let's say we have soil with PFAS having 200 microgram per kilogram concentration in it. For TCLP analysis, we take 100 gram of that. So for the sample that we use for TCLP has 20 microgram of PFAS. We add 2 liters of leaching solution on that, and then filter after TCLP. So if we assume that all 20 microgram of PFAS leaches to the leaching solution, it will go to 20 microgram per 2 liter, and it will be 10 microgram per liter. So maximum observable concentration in leachate will be 20 times less than we observe in soil. So, and then when we define leachability, we said what we measure in leachate divided by maximum observable concentration in leachate times 100 will give us leachability in percentage. So this is actually this graph shows all the data we have for this study. On the x-axis, you see different soil types. On the y-axis, you see leachability in percentages. And each dot represents a different PFAS. We also wanted to see different PFAS groups, carboxylic acids, sulfonic acids, and telomers, and to see if they behave differently during TCLP procedure. And if we check the box plots, the line here you see shows the median value. If you compare the median values of the different soil types, sandy loam have the highest leachability in terms of median value. But there's an interesting thing for sandy loam. The PFAS, different PFAS either leaches very well or doesn't leach very well. There isn't anything in between. And the sulfonic acids doesn't leach well from sandy loam. And the second one, the clay. For clay, there isn't anything we can say about how the different groups leach, how sulfonic group or carboxylic group or telomers leach, because the data is all over the place. They act differently even though they are in the same group. And organic soil, as expected, leaches PFAS less in terms of median value, but still there are some PFAS leaches from organic soil very well. Again, for organic soil, sulfonic acid forms of PFAS leaches looks like leaches less than medium values. So this is the whole data. When we focus on the hot PFAS, PFOS and P4A, when we compare that, there is a striking difference in terms of leachability. P4A leaches much better than PFOS from clay and sandy loam. And for organic soil, there's a similarity in between P4A and PFOS in terms of leachability, but still P4A leaches, we can say P4A leaches more than PFOS. Let's compare with the regulations. Yes, there are very few regulations about that, but Health Canada has drinking water maximum acceptable concentration for PFOS and P4A. Let's see how it gives us. PFOS, this graph shows PFOS leaching concentrations in clay. The soil concentration is 14.6 microgram per kilogram. So we expect to see, the maximum observable concentration is around 0.7 microgram per liter in leachate, which is higher than Health Canada drinking water maximum allowable concentration. But we measure less than 0.1 microgram per liter, which leachability, which corresponds to 15% leachability. It is very similar for sandy loam. 4.66 microgram per kilogram has 20% leachability. So they are very, very low concentrations. We thought the low concentrations give very low leachability. Let's see what will happen if we have high concentrations. So we expect more, and this is again clay. Soil concentration is 330 microgram per kilogram, 330 ppb, and still we have 18% leachability. So if we think that leachate toxic value is 100 times drinking water MAC value of Health Canada, to reach there, we need to see 6 ppm, 6,000 microgram per kilogram PFOS in clay. For high concentration in sandy loam, it is similar story with clay. Soil concentration is 196 microgram per kilogram, and we still have 20% of leachability. What about the P4A? P4A, as you remember, the leachability was way better than PFOS, and this is a comparison for P4A in clay. The soil concentration is 32.7 microgram per kilogram, and we expect the concentration in leachate way higher than Health Canada drinking water MAC values, and we observe it like that with 86% leachability. And it is very similar for sandy loam too. 15.4 microgram per kilogram soil gives 100% leachability, and it is higher than Health Canada drinking water MAC values. So these were PFOS and P4A. And when we come, today we listen to PFOS and P4A talks, and also Lindsay talked about what we should focus on, and there were lots of data about 6.2 FTS is coming, and we have some data about 6.2 FTS, and I want to talk about that. 6.2 FTS is the main component is of AFFF currently in use. So this box plot shows the leachability of 6,2 FTS, and again we see very high leachability of 6,2 FTS for all soil types, and it acts like PFOA. Even though it's a sulfonic acid, it leaches like carboxylic acids of legacy PFAS. There is one interesting story about 6,2 FTS. Its leachability is inversely correlated with soil concentration. So with increasing soil concentration, the leachability of 6,2 FTS decreases. But Health Canada has drinking water screening value as 0.2 microgram per liter. When we have 3.7 microgram per kilogram, we can hit the 0.2 microgram per liter screening value. If the soil concentration gets as high as around 200 microgram per kilogram, we may see 50 times of Health Canada drinking water screening value, but with the 40% leachability, it never reaches there. There is another interesting property of FTS, or different than PFOS and PFOA. It's not as stable as the legacy PFAS. So the telomeres are oxidized in the environment, and they are converted to carboxylic acids and sulfonic acids. So TOP-assay is a good tool to simulate or show that oxidation. So there are two different concentrations here, one low and one high concentration in picomolars here. And in leachate, we have high 6,2 FTS, and after TOP-assay, we see high PFBA, PFPEA, and PFHXA concentrations. So when it comes to assess the risks of 6,2 FTS contamination, we have to consider also short chain carboxylic acids, and they will be in the play too. So my few slides, my last few slides, conclusions. Leachability of PFAS depends on soil type and PFAS type. And PFAS in current AFFF's 6,2 FTS leach more than PFOS, regardless of the soil type. And while assessing 6,2 FTS contamination, we need to consider short chain carboxylic acids such as PFBA, PFPEA, and PFHXA. What we see from our old data, all the PFAS act differently. So we need site-specific data to assess best management options for contaminated soils, because their behavior also depend on the site and soil type. Our data suggests that a predictive tool can be developed using soil type and PFAS composition to account for contaminated sites, PFAS contribution to landfill leachate. And of course, we need further research with actual landfill leachate and groundwater samples. So our ongoing and planned work is shown here. It's a very similar scheme with our current work. We will use AFFF with and without PFOS and P4A, and we will spec different soils at different concentrations. But this time we will do SPLP instead of TCLP, because there are recent studies suggesting that SPLP may be more appropriate for assessing leaching of PFAS. I like to acknowledge our collaborator, Matrix Solutions, and Blake Hamer from Matrix Solutions, and my fellow authors from Agat Laboratories, Phil and Olivier, and our president, Brian Chubb, for his valuable comments during this study. I'm happy to answer your questions, or you can send me an email or call me if you have any questions. Thank you.
Thank you very much. Are there any questions for Eamon? Just give a second to see if there's any questions for you. I appreciate you doing this. Okay. Okay. It doesn't look like there's any questions at this time. Once again, feel free to reach out to him. His email address is on the screen. You'll be able to find it in the video as well. So we'll switch to our next presenter.
Thank you.
You're welcome. Thank you. Heather Lord with Bureau Veritas.
Thanks, Joe.
Yeah, give me a second here. You should have control.
Yeah, I think I do. I'm trying to get my screen to come up. There we go.
Perfect.
Okay, I think we're good to go.
Great. Thank
Okay,
you.
so yeah, thank you, Joe, and everyone at ESA for giving me this opportunity today to talk to you about our new total organic chlorine analysis. I'm Heather Lord. I've been with Bureau Veritas now for just over 8 years. I'm really excited today to talk about this new test. I think it's going to be a great addition to the PFAS. Okay, so now I just need to get my slides to advance. And they don't want to advance. Here we go.
Got it?
Yes. Oh dear. Okay, we still good? My screen just did something funny.
Yeah, so we just have a little bit of delay, but it's good.
Okay, fantastic. So brief outline here. I'm going to have a little bit of background history and why PFAS are somewhat of an environmental concern and all about the dark matter. I'm going to keep that brief. A lot of that has already been covered today. And then moving on to what the total organic fluorine analysis is. And finally, cover what our service offering is. So first off, some of the major sources of PFAS impacts. We've heard a lot about aqueous film forming foams, primarily from fire training centers or emergency response sites. So they're definitely one of the major sources that people want to keep track of, and certainly airports or any sites where there has been particularly a major petroleum fire. You're probably going to see some issues with PFAS on that site. Of course, industry. The industrial sites in the US where these compounds were originally produced, we're certainly seeing some significant impacts at some of these sites, even quite far down gradient from the sites. Now, there was no actual production of PFAS in Canada. However, we do have a lot of industrial sites in Canada that use PFAS in the production of other products or in their processes. So other speakers have mentioned today about different types of industries that are also likely to have impact at their sites if you're doing work on those types of sites. We've also heard a bit about wastewater treatment plants. Of course, PFAS that's used either residentially in our consumer products or industrially. will end up in a wastewater treatment plant. And the biosolids there are actually really good little bioreactors of converting the larger precursors into the sulfonic acids or carboxylic acid that we typically report on in our current PFAS analysis. And Jennifer really covered this well earlier this afternoon, so thanks for that. And then we heard, of course, excellent information from Edmund just now, talking about leachate, and particularly from landfills. Certainly all of our consumer products and a lot of industrial refuse ends up in landfills, and landfill leachate is largely captured now. Where does it go? It goes to those wastewater treatment plants. Interestingly, in most wastewater treatment plants, if you measure the PFAS in the influent and the PFAS in the effluent plus the biosolids, you can see a very significant apparent magnification between what goes in and what comes out. However, this is not because they're actually generating PFAS. It is strictly related to the breakdown of these larger PFAS compounds into the things that are currently being measured in our regular PFAS analysis. Again, thanks to Egmund for his introductory slides. I won't dwell on this too much. Where it all began was primarily the carboxylic acids and sulfonic acids and all of their related compounds. And then we very quickly realized we needed to also be monitoring the precursors. Some of those are shown here. And then as replacement products started to come out, there's of course lots of interest in monitoring them. As Bud pointed out, the toxicity of them is up for discussion. Some quarters say they're not toxic, other quarters saying not so much. And so we now have a number of these compounds, usually 30 to 50, reported in our typical PFAS analysis. However, it's well known there are at least 4,000 additional compounds out there. And that's what I'm referring to today as the dark matter. So as I said, about 20 to 50 PFAS typically reported in a standard PFAS analysis, but those additional 4,000 plus PFAS compounds, not only are they not reported because we don't have standards for them, but they're also not being reported because most of them are unknown or uncharacterized. There are a few labs that are very specialized that can report a couple of hundred, but really there isn't a good way out there to capture the total magnitude of this dark matter. However, they can be very difficult to deal with, not unlike our friend Darth Vader here. Sorry for that divergence. So yeah, PFAS dark matter can break down or transform into the PFAS that we are measuring, and they also can contribute to toxicity risk that is beyond what we're currently assessing with our standard PFAS analysis. So this causes, this is a source of the conundrum of how to deal with this dark matter. Because how do you accurately assess the site risk or the magnitude of remedial effort that might be required on your site if you don't know the magnitude of this dark matter? Of course, the total oxidizable precursors test that Egmund talked about, yes, that's been available now for a few years, and it's really helped to shine the light on what this dark matter is, or at least what the magnitude of what it might be. However, there are some recognized problems with the test. It's a nice tool to have. It's better than nothing, but it's not really all that quantitative in some cases. And most of us are seeing fairly high sample variability, particularly for things like soils. And it doesn't necessarily capture all the dark matter. It's really an unknown how much of that dark matter is actually captured in the total oxidizable precursors assay. So the industry now for the past few years has been looking at total organofluorine and the different methods out there as hopefully a better answer to what magnitude of the dark matter is. Well, last year there was a couple of really helpful papers that came out. Here's one that came out in Environmental Science and Technology Letters, comparing the three leading technologies for total organofluorine analysis. Method one is CIC, spoiler alert, that's the one we're coming to market, or we have come to market with. And then comparing to PIGY and neutron activation analysis. So I'll just go through what these three are. Combustion ion chromatography, or CIC, uses equipment very similar to what is in wide use, primarily in Europe, for adsorbable organic halide analysis. So it's instrumentation that's well understood. It's just up till now hasn't been well suited for fluoride analysis, at least not at the levels we need to get to. PIGY, particle-induced gamma ray emission spectroscopy, has been one of the leading methods in the industry so far to get a handle on total organofluorine. However, the equipment required is really only available in a few laboratories with access to this fairly specialized equipment. And neutron activation analysis, similar boat. It's a well-respected technology, been used for decades. We actually offer it here at Bureau Veritas Labs and have been for several decades. However, it requires access to a research-grade nuclear reactor. However, both PIGY and neutron activation analysis are relatively mature technologies. They're well understood. Nice thing about this paper that came out last year is it compared all three methods for their ability to assess total fluorine in a sample. And you'll see that all three lines line up on top of each other. So this was really, really great news to see that CIC is producing similar results to both PIGY and neutron activation analysis. So from there, now what we're looking at with this new addition to our toolkit is, of course, PFAS by LC-MS-MS isn't going anywhere. We're going to be offering it for the foreseeable future, and we're sure that regulatory requirements will continue to require that analysis. COPS assay also is not going anywhere. However, we now have this new tool that we feel, and what the industry is certainly hoping, is will give us a much better idea of the magnitude of dark matter on a lot of these sites. The other paper that came out last year that was very helpful was out of, I believe it was out of Germany. And this reported on really the first commercially viable CIC TOF method. There's been some advances in the technology of the equipment and some improvements in the way the method's done that were described in the paper that has allowed a relatively easy analysis for a production lab to get a total organofluorine. This paper was, the other output of this paper was it looked at total organofluorine versus the sum of PFAS by a standard LC-MS method in wastewater. And the black bars here in the bottom of this graph is the sum of PFAS from LC-MS analysis in each of these samples, expressed as the fluorine equivalent in the sample, because it's important to understand that the result you're getting from a total organofluorine analysis is fluorine, not PFAS. So then the CIC TOF method was also used on these samples, and the gray bars here shows the total organofluorine. You can see it's much higher in most of these samples and can be accounted for just from the sum of PFAS, again expressed as fluorine, that were measured by LC-MS. So just a brief word on what this method is. It's a semi-automated solid phase extraction, not unlike the solid phase extraction that's done in a lot of LC-MS PFAS analyses. It uses a different sorbent, but other than that, SPE is virtually identical workup. What this step does is it isolates the organic fluorine from inorganic fluorine, and that's really critical. you want to make sure that you're only reporting organofluorine, because a lot of water, for instance, have high levels of inorganic fluorine, and we can't have that confounding our PFAS number. And then next, there's an automated combustion. So the organofluorine that's isolated in this SPE step is burned in a furnace at 1,000 degrees C, where we know the organofluorine can be broken down into fluoride ion. It actually comes out as HF, hydrofluoric acid stream, and that's trapped in water. And then the system, after the combustion is done, the system automatically transfers that fluoride that's trapped in the water into an ion chromatograph, which is of course very standard equipment in any analytical lab. Anyway, getting back to this von Abercron paper, what they found is most of these wastewater samples had about 100 times higher organofluorine in them than could be accounted for by just the sum of PFAS. So this is the type of information I think is going to be very helpful for people going forward to get a much better handle on what the total organofluorine is. Now, the method that we're coming to market with, or we have come to market with, is actually described in this Thermal Scientific Application Note. It was published in the spring of this year. It's available online if you'd like to download it from the Thermal Scientific website. It's freely available. It does follow almost word for word what is reported in the von Abercron paper. So really the Thermal Application Note and this 2019 paper are essentially identical, and that is the method that we have developed. So a little look at what this equipment looks like in our lab. First of all, the semi-automated SPE. So water samples are passed through these SPE cartridges that you can see in the upper right of this screen. And the organofluorine is trapped in the cartridge, and the inorganic fluorine is sent to waste. The sorbent in the cartridges is then loaded into boats on a combustion auto sampler, and those boats are sent one at a time into a furnace where the sorbent is combusted. The hydrofluoric acid stream is trapped here in this HF absorption unit, and then we have a standard ion chromatograph on the end to do the data analysis with. So the first question that comes up for most people is, okay, so what do my TOF results mean? How can I take a TOF result and understand what that may mean to how much organofluorine is in my sample? Well, here's a rule of thumb for you. I'll show you how this calculation is done with PFOS, but it really applies to virtually all organofluorine. So PFOS here, it has a molecular weight of just about 500. However, we can see from this equation, it's got 17 fluorines. We can count them here. Well, the molecular weight of 17 fluorines is 323. If you take the ratio there, 64.7% of a PFOS molecule is fluorine. So if you get a total organofluorine result of 162 nanograms per liter, that's going to be equivalent to, if it's pure PFOS, 250 nanograms per liter of PFOS. Now, of course, different PFAS molecules have different numbers of fluorine. But for the sulfonates and the carboxylic acids, this number of 64% holds very well. And then for larger precursors, it's a little less, 55 to 60%. The general rule of thumb, 60 to 65% if your sample is mostly acids, or 55 to 60% if you've got a whole lot of precursors, but that's a pretty good rule of thumb to help you gauge what your equivalent PFAS level would be in your sample. I'm just going to do a quick time check here, not too bad. These are some submitted client samples, of course anonymized here, that we have run LC-MS analysis with and calculated the sum of PFAS. Next column is the calculated organic fluorine in the sample. We didn't apply just the 60 or 65% rule here, however. We actually calculated out the mass of fluorine in each of these samples based on what we saw with the LC-MS analysis. So you'll see those equivalent fluorine numbers here in this middle column. We then did TOF CIC on them, and you'll see in the next column how much organofluorine we actually saw. So the first sample here was submitted. The client identified it as field blank, and we did find that it came back at less than detection limit. Now our reporting detection limit that we're going with is 2 micrograms per liter. We are finding that this is due to background fluoride in the carbon. And we do see that looking at the background fluoride in the carbon is the most likely way to get reporting limits below 2 micrograms per liter. That's where we're at for now. And really, I think that should be helpful in a large number of cases. Here's sample 2, however, and you'll see that LC-MS analysis said that this sample was virtually non-detect, about 2 parts per trillion here, below most regulatory guidelines. So most people would have passed this off as being clean. Calculated organic fluorine here, about 1 part per trillion. But here, look at this, we got 1,000 times higher. We definitely saw a very measurable signal in the total organofluorine analysis. So definitely there's chance of seeing that samples that were previously gauged as being non-detect do have measurable organic fluorine. Now, yes, this was below our reporting limit, but still, that's it was definitely a noticeable signal. Here's a couple of others, just to kind of delve into what the challenge will be if you want to try to assess your total PFAS based just on LC-MS results. So look at samples 3 and 5. 5 appears to have way more PFAS in it than 3. However, by total organofluorine, we see that they're virtually identical. It's just that 3 had a lot more dark matter in it than 5. So 5 was about equal. There was essentially no dark matter in 5. It all transformed to organofluorine and consistent with what we were expecting. Versus 3, we got almost a 50 times increase. Here's another couple samples, 6 and 7. They're fairly in the same order of magnitude of PFAS, the LC-MS, between 2 and 10. However, we saw over 10 times increase in organofluorine from one sample and only a 2 times increase in another. So this just shows you what kind of information you can get from TOF. It is really almost impossible to gauge by just looking at some of PFAS results. Here's some more samples. So I've broken these samples down a little bit by, how much PFAS, how much HXS is in it, and how much precursor. Because you might say, well, if my LC-MS results says I've got a lot of precursor, there's probably going to be a lot of other dark matter in there. I will note these 3 samples, we did look for a fairly large suite of precursors. We only saw 4,2 and 6,2, so that's why the precursor column is only 4,2 and 6,2. So water 1 here definitely had precursors in it. Some of PFAS by LC-MS should have been about 16 micrograms per liter. Convert that to organofluorine around 10. We saw about double that though. So there were other precursors or larger compounds in there that raised the total organofluorine about 2 times over what we were expecting. This other water had no measurable precursor in it, however. It did have PFAS and HXS, and that saw over a 10 times increase, over 10 times higher total organofluorine than could be accounted for with LC-MS analysis. So in this small subset, we're not seeing too many that are in that 100 times higher, but we're certainly seeing a lot of them that are in the 10 to 50 times higher. So it'll be interesting to see a larger number of Canadian wastewater samples see how much that dark matter is in Canadian wastewater compared to what other jurisdictions are seeing. I just now want to talk about this AFFF sample that we received recently. We know what this product was. It's a commercially available AFFF. It's actually marketed as a biologically friendly, environmentally friendly, biologically biodegradable, non-toxic PFAS. Neither the documentation that came with it or the SDS mentions anything about it having any PFAS in it. However, we found 53,000 micrograms per liter of 6,2 FTS. That's pretty much the only PFAS we found in it was 6,2 FTS at a fairly high level. Some of PFAS converted to organic fluorine says we should have seen about 30,000 micrograms per liter of organic fluorine in it. However, we actually saw 7 million. So a 200 times increase in this AFFF that was supposedly PFAS free and environmentally friendly, non-toxic, biodegradable. So I found this very concerning. I don't know how widespread this is with AFFFs that are being sold as PFAS free that aren't, but I thought that was very nice to be able to pick that up relatively easily. So just doing another quick time check here. It looks like I've got about 10 more minutes. So getting into now what this is going to offer to the industry. It will, we believe, increase the reliability of PFAS impact delineation. It should be much easier to fully delineate the extent of PFAS impact on a site and increase accuracy in estimating required remedial effort and costs on these sites. Have a much better handle on the magnitude of PFAS on the site. It should help also in improving remedial progress. So if you're doing a pump and treat and you're wanting to monitor your effluent stream from your pump and treat system, I think this will make it relatively easy to monitor if you're getting efficient recovery of PFAS in that treatment train. We do expect a reduction in cost. The cost we're coming to market with is about half the cost of a standard PFAS analysis. Of course, if you want to do a TOPS assay, that's usually double a PFAS cost, so that will significantly reduce the cost of trying to get at the dark matter. We're hoping to get a little faster turnaround time than we're currently able to offer with LCMS analysis, and we think it could possibly also simplify AFFF evaluation, particularly as people are trying to evaluate their stock, find out if they're actually PFAS free or not. However, I mentioned LCMS analysis is not going anywhere. It does have still a lower detection limit than POF by a couple of orders of magnitude. It will definitely be around for the foreseeable future for regulatory compliance and risk assessment. However, in terms of the ability to understand your total PFAS contamination, TOF, I believe, will take the show there. And of course, I think it'll be very helpful in determining, is my AFFF actually PFAS free? So sample submission information. We need a little larger sample volume right now than we do for PFAS analysis. We are following that application note fairly closely. We've only had, we've got this to market. We got our equipment in July, so we're bringing it to market fairly quickly. So we haven't made any modifications or optimizations to that application note. And so that's where the 250 mil comes from. We hope we can reduce that with ongoing method development, but that's a good start, I think. 2 bottles of that, please. AFFF, of course, we don't need nearly as much. We have to dilute it so far to get it in the calibration range. But yeah, so if you're used to sending in a 125 ml bottle of AFFF, that's fine. All times, these samples are actually preserved. Both the application note and the ISO reference method that is followed for this analysis specify preservation with nitric acid, which allows us to hold these refrigerated a little longer than the unpreserved samples for selecting for PFAS analysis. Of course, AFFF will have indefinite storage or hold time, or as specified by the supplier. TAT, very comfortable. A 10-day TAT will be fine. If there's a super rush going on, we think we can turn this around in 3 days. So the next steps, I said we haven't done a lot of optimization or very little optimization on the on Abercron paper and application note. The equipment is set up and validated. It's passed our internal validation. We've got our customer sales and customer service and sales teams educated and brought up to speed on what this is and how to help everybody understand the method and what it could potentially offer to sites. We're working on some case studies. We've got presentations. We have this webinar that I'm doing now is available on demand from our website, and we went live this week. We're now ready to accept samples. However, there is a phase 2 that will be underway shortly. We want to do some things like shortening the run times. The technical application note does have a rather long run time. There's other papers out there saying we should be able to shorten it. We'd like to do that to increase our throughput. There is a little bit of concern. If you take a look at that application note, there's a suggestion that higher molecular weight PFAS may actually have lower recovery. So we want to delve into that to understand it a bit better and bring out some information and exactly what recoveries of higher molecular weight PFAS are in real samples. We also would really like to reduce the detection limit. We'd like to try to see if we can increase the sample volume, improve instrument precision. We think that will help us somewhat there. And of course, if we can get the chlorine background down in the carbon, that would be great. Right now, we're coming to market with water and AFFF only. That's what was described in both the research paper and the application note. We do see some other question marks with extending the method to soils quickly. But we are definitely working on that, and we'll bring it to market as soon as we can. So with that, I'd like to wrap up and thank the people that have been involved with this. Lucy Catchatrain, that works with me here in Mississauga, she has done the lion's share of this work and has just done a fantastic job of making this a reality for us. And our collaborators at Thermo Scientific for help with the IC and the thermal application note, and Mandel Scientific for help with the combustion system. Thanks go out to them for helping to make this a reality for us. So finally, if you want to reach out to any of us, there's lots of contact information here on this slide. We've set up an email address, pfas@bvlabs.com. Of course, it's for all PFAS questions. But right now, of course, everybody is set up to answer questions on the new total organofluorine analysis. This email goes to our customer service people across the country and will be vetted, and the person that gets back to you will be someone local for you. If you have any more technical questions, please feel free to reach out to Stephanie Pullen. She's our senior account manager for our PFAS analysis. And myself, you'll have my contact information here, and Terry Obel, our chief science advisor. Thank you very much, and I'm certainly happy to answer any questions if there are some.
Thank you, Heather. It's very exciting for you guys. Interesting stuff. Any questions for Heather before we move on to our final presentation of the day? Okay, I don't see anything coming in, Heather. As usual, the emails are on the screen. They'll be in the video. You can reach out to Heather, and she'll be happy to answer questions.
Thanks very much, Joe.
You're welcome. Okay, we'll move on to our final presentation. I've left the lawyers for last. I didn't do that intentionally. It just worked out that way.
Sure, Joe.
Sure, yeah. It seems like I always do that. So we have Matthew Gardner and Jacqueline Stevens from Williamson Shire Environmental Lawyers in Ontario, also with offices in Alberta. They're going to kind of do a legal overview and kind of wrap up the day, and then I'll be back for any questions and some wrap up. So I'll turn it over to you both.
Great. Thanks very much, Joe, and thanks everyone for participating in the presentation all day. It's been a long day, but hopefully you've gotten some interesting insight. So Matt and I are going to give you a bit of an overview. Now, at the end of the day, we're just going to sum up a lot of things that you heard earlier today. And hopefully at the end, Matt has a bit of a case study to review with us in terms of some legal questions, as opposed to perhaps the technical side of things. So I'm just going to turn off my webcam and we'll get started. So as I mentioned, we're going to focus on legal perspective, and we will have a look at, oh, Joe, I'm not, oh, there we go, sorry. First, we'll have a look at pollution prohibitions. They're a bit of the base of what we're dealing with. Then we'll review quickly federal, provincial, and some US developments, as I said, which you've heard a lot more about earlier today. Matt will look at a case study for us, and then we'll give you a few key takeaways from our presentation and from the day today as a whole. So the first thing I want to just remind everyone about is environmental liability. And there's kind of two flavors that we worry about at this point. There's three if we're talking about consultant liability, but that's not today's subject. There's regulatory liability and there's civil liability. So the regulatory liability relates to what a regulator can do, be it Alberta Environment and Parks, the Alberta Energy Regulator, the Ministry of Environment, Conservation and Parks in Ontario, or Environment Canada, for example. And regulators can issue orders. They can also prosecute under the various environmental statutes. And orders can be issued to current and former owners, occupiers, and persons who have or have had management and control of a property or of an environmental issue. And these orders can require a person to investigate, remediate, prevent further migration of contamination, conduct ongoing monitoring, clean up a spill, even reimburse the regulator for costs if the regulator did work. And then the regulator can also prosecute for the offenses that might exist under the environmental statutes, be they failing to comply with an order or contravening a section of an act, for example, a spill section where it says you shall not spill or you shall report if you do. And there can be convictions of these prosecutions can lead to fines and sometimes even imprisonment. The civil liability relates mostly to contamination on site or contamination that's migrating from a site and impacting an off-site property. It also can incorporate concepts of a flow-through property, the guy in the middle or monkey in the middle, if you want to call him that. Not the source property, not the ultimate end property. And within this area, there are certain causes of action that are pled. Most commonly, we see negligence, nuisance or trespass, which is the unreasonable interference with the use and enjoyment of land, strict liability, breach of contract, and breach of statute. And the result is damages, be it the cost to investigate or remediate, the cost to prevent further migration, a cost for stigma or diminution in value, maybe health risks or business losses. And I just want to make a particular note in that each of these types of liability can be both corporate, so the corporation can receive, orders or prosecutions or be sued, but equally individuals. And that's where it comes in that former owners and officers and persons with control can be pursued by the regulator, and they can also be sued. And there's been at least one case recently in Ontario where a corporate director and officer was found liable in a civil claim, and that was done by piercing the corporate veil. So that's just a reminder about environmental liabilities.
Thanks, Jackie. So I'm going to speak now to pollution prohibitions, which really form, I would say, the basis or the core of environmental laws in Canada, both provincially and municipally, but also federally. And again, regulatory liability that is really founded on these pollution prohibitions and reporting obligations, again, comes in those two forms that Jackie went through: prosecutions, which are charges that could give rise to fines, and in the worst cases, most egregious circumstances, jail, very rare for environmental offenses, and then orders as well. So pollution prohibitions in Canada and provincially, in Alberta, in Ontario, across the country, and then municipally as well, can include different types of orders: stop and control orders, prosecutions in different forms, some just by whoever the environmental regulator happens to be, with the mandate or jurisdiction over the issue, the spill or the discharge, the leak or the emission to air, water, land, but also prosecutions and orders, frankly, in different circumstances where there's compensation needed to reimburse individuals who may have taken certain steps to remediate spills or discharges. We call those private prosecutions, and they're available in certain statutes in Canada. And then also government orders and prosecutions as well, to try and get back damages and costs that are incurred to remediate spills and discharges. So why do we care? The question today is really about emerging contaminants, and for Jackie and for me, we're talking about PFAS-related compounds specifically. And the point is, after we've gone through all of this fairly general environmental law that many of you on the web right now have probably heard from us before, the point is that all of this applies to PFAS, regardless of whether, and we'll get into this in the BC context, which we've heard about already today, regardless of whether there's a regulatory standard for contaminated site purposes. It doesn't matter, because PFAS can be, and the various compounds and forms that it can take, can be deemed a contaminant when they enter the natural environment and may cause an adverse effect. So let's go to an example in Alberta. Next slide, Jackie. Thank you. So here on this slide, we see that in Alberta, we have under EPEA, Environmental Protection and Enhancement Act, the primary environmental statute in Alberta. There's two major parts to it that are these pollution prohibitions. The first is the prohibition from releasing or permitting of the release, if you have any control over that release that happens, whether you're the actual releasor or not, into the environment of a substance in any amount, concentration or level, or at a rate of release that causes or may cause a significant adverse effect. And then there's the reporting obligation underneath that states that any person who releases or causes or permits the release of a substance into the environment that may cause, is causing, or has caused an adverse effect must report that release to Alberta Environment and Parks. So under EPEA, PFAS can be considered the substance that can give rise to significant adverse effects, and therefore could be subject to this prohibition and this reporting obligation if it's released into the environment. Here are three terms, defined terms within the slide that we just saw before: the pollution prohibition, release prohibition, and the reporting obligation. So these are all defined terms: adverse effect, substance, release. And all, in particular, I would say adverse effect, are quite broad under EPEA in Alberta and cover off PFAS certainly, so long as there is actually a discharge or a release of PFAS containing compounds, whether it's pure PFAS related compounds or the PFAS is contained in a different substance, where that release actually enters the natural environment and can cause adverse effects. So it's a pretty easy test to meet. And so this prohibition applies to PFAS just like it does to fuel, to CVOCs, to chlorinated solvents, dry cleaning chemicals, all of the usual suspects. Ontario's environmental regime, just for a second example, and we're not going to go through the whole country, but is very similar to Alberta's. Applies in the exact same way to PFAS and related compounds. And in Ontario, we have the Environmental Protection Act, which contains, again, a pollution prohibition that applies to all contaminants, including PFAS. And it's very similar to what we see in Alberta. And it also contains, and it being the Environmental Protection Act in Ontario, contains 2 reporting obligations, one for discharges, the other for spills. And the spills reporting obligation is not on the slide for brevity, but it is similar to the discharge reporting obligation, just in narrower circumstances, because spills, as you can imagine, are defined in the EPA in Ontario as arising from discharges from containers, vehicles, or structures. So it has to come from a tote that gets punctured by a forklift, comes from a drum, something like that. It's an active spilling versus discharges, which can be much more passive and cover off a lot of different scenarios. And either way, whether you have a discharge or a spill, it's reportable to the Ministry of the Environment, Conservation, Parks, just like it is to Alberta Environment and Parks in Alberta. So here are just defined terms, just like we went through for Alberta: adverse effect, contaminant, discharge, all of which are included in that discharge prohibition, all of which are included in the reporting obligations under Ontario's Environmental Protection Act. And the point here is that, like in Alberta, these definitions are very broad. There's a little bit more meat on the bones, I would say, with the 8 different ways that you can find yourself having caused an adverse effect versus Alberta's, which is much more general and broad, but both are so wide open and expansive that certainly a PFAS related compound will fall under the definition of adverse effect if it gives rise to any of these things and if it's into the natural environment. So another layer, and we're just kind of lumping this all in to be for completeness sake, I would say, but another layer of statute and bylaw legislation in Ontario is our water-related statutes. So just like Alberta's EPA and Ontario's EPA, there are federal, there are provincial, and even municipal water-specific statutes that are environmental statutes, very important, with regulations thereunder, and of course municipal bylaws that prohibit discharge of contaminants, including PFAS and related compounds, and the obligation to report to the regulator, whoever that may be, for discharging or spilling. And so, for example, federally, we have the Fisheries Act. It applies to discharges of PFAS to waters, bearing fish or fish habitat. And by the way, just to be very clear, the Fisheries Act, EPA, and Ontario's EPA, and the further statute and the bylaws that we're speaking to on this slide, Ontario Water Resources Act, municipal bylaws like sewer use bylaws, none of them contain the words, the full spellings of PFAS, PFOA, PFOS, PFBS. None of them do, or very rarely would they. And that's because it's not necessary. To regulate all compounds and all different types of contaminants and substances is easier to do when you're general about it and vague and broad in your language in your statute. And that's exactly what we have here. Municipal bylaws are interesting because they have both discharge prohibitions and reporting obligations for discharges to storm sewers, to combined sewers, to sanitary sewers of contaminants. And whether it's explicit in the bylaw or not, and I haven't seen any bylaws off the top of my head that are explicit to PFAS related compounds, but there may be some now, there may be some in the future, but certainly the provisions of these bylaws, if they are broad enough, just like the other statutes we've been through, can apply to PFAS too. Over to you, Jackie, to talk about the Canadian Environmental Protection Act and its explicit references to PFAS related compounds.
Great, thanks, Matt. So you heard today from Environment and Climate Change Canada and Health Canada about the federal perspective. You heard from Lindsay at SLR about the BC perspective, both this morning, and then from Jennifer from Geosyntec this afternoon about the US perspective. So I'm just going to remind you of some of those key elements. They would have had much more knowledge and done a far more detailed review than I propose to do here. But this is just a reminder, keeping in mind the different areas of law that you may have to look at, not only as Matt was talking about in terms of pollution prohibitions and the broad and general, but also the more specific. So starting with federal, both PFOS and PFOA are listed in the Canadian Environmental Protection Act's list of toxic substances. And under CEPA, that's the acronym for the Canadian Environmental Protection Act, it allows a minister to post a notice that can require a person to create a pollution prevention plan or an environmental emergency plan for any substance on the toxic substance list. And the minister may require a pollution prevention plan for a substance that I mentioned on the list, released from a source in Canada and may reasonably be anticipated to create air or water pollution outside of Canada, and released from a source in Canada that may reasonably be anticipated to create air or water pollution that violates an international agreement. Additionally, environmental emergency plans are typically required for emergencies where there may have been an immediate or long-term harmful effect to the environment, where there's constitutes a danger to the environment on which life depends, or it constitutes a danger in Canada to human life or health. And these are the tools in the minister's toolbox that can be implemented quickly, perhaps much faster than a particular regulation. PFAS are also listed in the prohibition of certain toxic substances regulation, and this regulation prohibits the manufacture, use, sale, offering for sale, or importation of PFOS and PFOA or a product containing them unless the substance is only incidentally present. And as lawyers, we always like to have clean definitions for things, although as Matt was saying, some of them are really broad, which might be good for your client or might be bad. But incidental presence is generally understood to be a residual, a trace contaminant, or an impurity that was not intentionally added to the formulation. So incidental presence exceptions don't apply to the substances that are listed in Schedule 2, Part 3 of the regulation because they have permitted concentration limits. The exceptions that I mentioned, there are some, there's a few, just to highlight a couple. PFOS in photographic films, paper and printing plates, PFOS in aqueous film forming foam present in a military vessel or military firefighting vehicle that were contaminated during a foreign military operation. Who knew? PFOA in aqueous film forming foam used in firefighting. So those are the types of exceptions that exist. Then at a federal level, we also have the Federal Environmental Quality Guidelines, which are recommendations that are there to support environmental quality monitoring. They're intended to be set such that where the concentration of a chemical is at or below the FEQG, there is a low likelihood of a direct adverse environmental effect. These are, however, they're voluntary guidelines unless they're otherwise prescribed by a permit or other regulatory tool, and they're intended to protect aquatic biota and wildlife that feeds on aquatic biota. And some of the concentrations are for surface water, 6.8 micrograms per liter, fish tissue, 9.4 milligrams per kilogram, wet weight. Wildlife diet, a mammalian diet is 4.6 micrograms per kilogram wet weight in food. For an avian diet, it's 8.2 micrograms per kilogram wet weight in food. So there are some guidelines there in terms of, in particular here, in terms of aquatic biota and wildlife that feeds on that aquatic biota. We also have guidelines for Canadian drinking water quality from Health Canada. These are created based on research related to health effects, aesthetic effects like taste and odor, and operational considerations. Health Canada's guidelines are also not legally binding on their own. Instead, they're intended to inform provincial drinking water standards. So the Canadian Drinking Water Quality Guidelines establish some maximum acceptable concentrations for a number of chemical and physical parameters. And currently for the PFAS, in particular PFOS, is 0.0006 milligrams per liter. And if my math is correct, that's actually parts per billion. I'm not a chemist. I'm not a mathematician. I'm a lawyer. Anyways, you get the picture. PFOA is 0.0002 milligrams per liter. So those are the types of guidelines. Health Canada also has screening values for PFOS and PFOA, and has soil and drinking water screening values for 9 other PFAS chemicals as well. The screening values are developed at the request of a federal department, province, or territory when there is a need for a quick response and there are no existing formal guidelines. These screening values don't necessarily or don't typically undergo peer review or public consultation as more formal guidelines would. They're often an immediate response type guideline that is available. Matt?
Unmuted. Okay. So this is a summary of just a list of which provinces have implemented specific regulatory concentration limits on PFAS compounds for contaminated sites, redevelopment, and other aspects of contaminated sites statutes and regulations. And as you can see, BC is the only province so far to regulate PFAS for that contaminated sites purpose. This is a very simple decision-making pathway that is from the BC government of how BC's contaminated sites legislation works. And the only point here is just to describe to everyone who may not be familiar with BC and its regulatory regime for impacted sites, that there's a screening stage at the outset where the proponent, the property owner, the company is required to submit what's called a site profile to BC's Ministry of the Environment. And this legislation, and we'll get into the meat of it in a second, is again applicable to all contaminants for which there are prescribed regulatory concentration limits for contaminated sites redevelopment purposes. And this is for BC specifically and applies to 3 different PFAS compounds. So the overarching framework starts with BC's statute. It's primary environmental statute, just like a PIA in Alberta, and it's the Environmental Management Act. And it sets out when a person, company, proponent, owner is required to submit what BC calls a site profile. That site profile is required typically for redevelopment purposes. The same sort of thing we see in other provinces with records of site condition, remediation certificates and the like, for zoning, for redevelopment, for demolition permits of the structure, for soil removal. And the BC director at the MOE there may order an investigation if the director reasonably suspects, based on the site profile, that the site may be a contaminated site, which means it has elevated concentrations of any of the contaminants for which there are applicable standards, and we'll get to that in a second, or contains substances that may cause or threaten to cause adverse effects on human health or the environment. So it's broad, another broad term that's a catch-all. And this is relevant to PFAS generally, and the 3 specific PFAS compounds that we'll get to in a second, because again, there is an actual prescribed regulatory concentration limit for these PFAS compounds, and so they're subject to this regime. Next slide, Jackie, for regulation. Yeah.
Yeah, I'm trying. Hang on. Yeah, I can't get it to advance. Why is it not advancing? Page down, page down. Oh, this is not. Sorry, everyone. Oh, there it goes.
It worked. Thanks. So the contaminated sites regulation is really the meat of the BC contaminated sites regime under the Act, and it contains specific numerical standards, concentration limits for PFOS, PFBS, pardon me, in soil and groundwater, and then for PFOA in groundwater only. And the point of this regime is that if there's an investigation, site assessment at a site where these concentrations of substances, of these substances at the site are above that prescribed numerical standard, that limit, the site is deemed contaminated. And then there are further steps that can be taken by the ministry as a result of that. So the way that the regulation works is it has actually a number of different schedules, and it's very well laid out through BC's website, but the water standards are listed in Schedule 3.2, soil standards are listed in Schedule 3.1. And what's most important, and ties in actually with the case study that we'll get into in a second, is that there are prescribed circumstances and carve-outs and exemptions for which types of contaminants, including PFAS compounds that we went through, the 3 of them, may apply or may not apply for this regime. So the water standards, for example, only apply to sites, properties with specific, we call them Schedule 2 activities. So enumerated list of different types of activities that fall under Schedule 2 of the regulation. And those are, as you can see here, fire retardant manufacturing or wholesale bulk storage, metal plating, as in chrome plating or metal finishing industry. And that's the case study we'll speak to in a second. Aircraft maintenance, cleaning or salvage. And last but not least, and probably most interestingly, because the first 3 I've gone through are those types of industries where you often will see PFAS compounds used or historically used for those purposes. But there's also sites which have been or are likely to have been contaminated by substances migrating from other properties. So there's a catch-all there where you have the potential for adverse effects because you have contamination from one site migrating to another, which triggers all sorts of liabilities that Jackie and I basically, earn our paychecks trying to resolve and deal with, both regulatory and civil. So cross-property boundaries is a catch-all where even if it's not any of those other types of industries, if you have PFAS that's migrating across, it applies. The standards apply. Okay, Jackie, over to you to talk briefly about the US.
And I'm having troubles again advancing my slides. Not sure why. So I'll just talk for a minute. The jurisdiction in the US, as we heard from Jennifer, is far more active in regulating PFAS. We had the interim, sorry, my whole computer seems to have frozen. We had the interim recommendations back in December of 2019 from the US EPA, and then the action plan, and they provided the update in 2020. And that was to prioritize health impacts and addressing groundwater, in particular that is current or potentially a source of drinking water. And in addition, and Jennifer highlighted a few of these things, the US EPA is looking at more enforcement and using the US Safe Drinking Water Act. It's using that to issue orders and to enforce the requirements. It's setting a recommended screening level of 40 parts per trillion to determine if PFOA and or PFOS are present at a site and warrant further investigation. And those are risk-based values. It's also using EPA's lifetime drinking water health advisory of 70 parts per trillion as the preliminary remediation goal for contaminated groundwater that is current or potential source of drinking water. And then there's a few other action items that they've also been advancing, dealing with drinking water specifically, cleanup, monitoring, the toxics release inventory, and surface and water protection and research. And Jennifer provided those, lots of details about some of those earlier this afternoon. And I still have no control over my, oh, there we go. Try again. Okay. I just wanted to briefly mention, as Jennifer's already covered it, the 2020 National Defense Authorization Act, and that requires DoD to take certain steps to phase out PFAS in firefighting operations. And it also is adding it to the toxic release inventory, which is similar to Canada's NPRI, that can retrigger reporting obligations for companies and may inform future legislative action. Additionally, just very quickly, and Jennifer touched on this, there's about 24 different states that either have guidelines or standards or in draft or they've been set, and they include drinking water, groundwater, surface water limits. But as Jennifer mentioned, there's an issue because they don't all include the same PFAS compounds. They don't all use the same standards. But the reality is it's still more advanced than we are here in Canada. And this is just a table to compare some of those values. They're not exactly equivalent, but it gives you a general idea of a few different jurisdictions about safe drinking water. And you can see that in BC and Canada overall, the concentrations that are set as acceptable are not as stringent as those that we see in the US. So we wanted to just touch on, bring together a number of the different presentations we saw earlier today. I think Matt gave a presentation, the other Matt gave a presentation looking at how do you approach this problem, and there's kind of a method to it, but you'll notice that it's not so different from any other contaminated site. So it's not that PFAS are different in the way we approach the solution or the problem. It's just that they maybe are a little more difficult to deal with. So there's still the requirement to consider the source. And Matt touched on a few of those. There's a requirement to develop your conceptual site model. You have to do the background work, the legwork, do your analyses, figure out your types of PFAS, do your fate and transport analysis, consider migration pathways, exposure, receptor and exposure pathways, look at the toxicity reference values, which aren't all that well developed. And then the next step, of course, is to consider what remedial options might be available. And we've heard from Imogen and a couple of others about new ideas that are coming about to try and figure out ways to treat PFAS compounds. And then there's the issue of maybe you need to do a risk assessment and you have to know about the boundaries and the reference areas, and then your toxic reference values. Matt, over to you for our case study.
Thanks, Jackie. I'll be brief for sake of time. What happened in this particular case, and what is happening, because it's an active one in Ontario, is that we have a client who's a chrome plating facility. So this is one of those industries that I spoke to earlier that's being specifically regulated for the purpose of water in BC, and for good reason and for not good reason, because in our case, our client does not use PFAS in any of its operations, but certainly in the past, and this is why the neighboring property owner and the Ministry of the Environment, Conservation and Parks, through a voluntary abatement process, a voluntary remedial process, have urged through this injection program that we're in now, before the actual injection work is done, baseline investigation work, that PFAS should be one of the contaminants of concern that should be sampled for, in addition to hexavalent chromium, which is the primary contaminant of concern. Why, you may ask? And the reason why, I will tell you, is because chrome plating operations, due to, at least in the past, and maybe certain operations still, can use surfactants and for fume suppression purposes that do contain, or did historically contain, PFAS components. So in our case, frankly, I have way more questions than answers, which is a good lawyerly thing to do. Ask all the questions but don't have the answers. And some of those questions are as follows. Is the PFAS from the operations either that our client's undertaking now or any of the predecessors at the property actually from those operations? Or is it from some other source? Is it up gradient as opposed to within the contamination zone? Should we be sampling both in the contamination zone and up gradient to determine if potentially this PFAS is ubiquitous in this area, as it often is in the environment, for all the reasons we've heard today? And if we do find it in both contamination zone that we're looking at to remediate, where the hex chrome is, but also up gradient, what do we do about it? Is it something that we can risk assess? Is it something that we can apply risk-based standards to? There's no benchmark in Ontario like we have in BC for contaminated sites. There's no specific numerical standards for PFAS-related compounds. What do we do when we consider how the geology, which in this site is fairly tricky, clay, silt, fractured shale bedrock, what do we do about it, and how do we remediate if we're even going to be able to? Is there an appropriate remedial technology that's just starting to be unveiled that will actually knock concentrations down? if that's something that needs to be done. And lastly, and probably most importantly in my view, if this stuff is so ubiquitous in the environment and in the subsurface, does our client actually need to clean it up? And is there any effect on human health or ecology? And because our client's not the polluter per se, because they're not the causer or permitter of the PFAS in the environment, if it is indeed upgradient, what do we do about it? And that's going to be a dialogue that we have with the regulator, with the neighbor, while we undertake the process of tackling the more, frankly, important hexavalent chromium issue. So that's a case study that brings up a lot of questions and then really segues into our key takeaways.
And I can't change the slide. I'm very sorry about that. The key takeaways, though, we don't have standards across Canada to use that are binding. We have some guidance. More work needs to be done, and that just goes to show that this is still an emerging contaminant. We are learning more, and we have learned lots, but it's still emerging in terms of both regulations and in terms of technical solutions. But as we said early on, provincial laws still prohibit pollution releases that cause or may cause an adverse effect. So even though standards or guidelines might not exist, you may still be required by the regulator to do something. And maybe, unfortunately, that could mean a full cleanup, or maybe it's a risk assessment, or it's something else. But the main key takeaway really is that you need to ensure you have your technical and legal support early on so that you're understanding the problem and you're understanding what those potential solutions are as you're addressing the site conditions. And that's it from us. And I would put up our contact information if I could get my system to respond. Apologies for that.
Jackie, you have no luck with this every time.
I know, every time, Joe.
I don't know. Maybe they should get you a new computer. I don't know. Just saying.
Yeah, I'll talk to them, believe me.
I really appreciate it. Good way to wrap up. We have one question. Don't know if you'll be able to answer it. Even if the product is ubiquitous, what happens if the down gradient concentration is much higher than the up gradient concentration?
Right. Great question. It comes down to the last takeaway that Jackie went through, and that is we need to engage the technical support, the legal support. And it's an interesting one because I think we would need to try and figure out if the PFAS compounds that are in the subsurface at that point in time that are higher in concentration down gradient actually are attributable to the property owner or the predecessor in operations at the property. Because if they're not, and it's actually the same compounds that we're seeing up gradient, but for some reason, maybe because of groundwater, because of collecting of the impacts at the site, because of the geology, if there's some sort of a bathtub effect. Like, these are all the technical inputs and the great questions that I get to ask and don't need to answer of our consultant and our remedial contractor. And that's a discussion that you have with all the stakeholders, the regulator, the neighbors, whoever it is who's involved.
Okay.
Great question.
Adverse effect is very broad, as you've noted. Can you provide examples of how this was successfully litigated for an emerging or non-regulated substance, or provide examples of types of demonstrated adverse effects that would likely support successful litigation?
Well, the case study, although not litigation, is one example of it's not a regulatory action, but the regulator is involved. And the neighbor who is working with our client, and this happens all the time on a voluntary abatement approach is what we call it, with all of these different parties involved pre-litigation. And I don't, hopefully we'll never go to litigation because it's expensive and nobody wants to pay the lawyers for all of that if you can avoid it and get to the environmental solution instead, is one example where we have an emerging contaminant that is now the subject of, and really is secondary to the primary contaminant, which is hexavalent chromium. So I think that, frankly, that's the first file that I've been involved in where PFAS has become part of the discussion and part of the legal realm of the file, but it's going to happen more and more often for sure. And I'm sure that there are other examples in our office, and other environmental lawyers would have other examples where this is becoming more of an issue. But the hook, again, and to the point of the person who's asking the question, and I agree, is that these pollution prohibitions apply very broadly. And as long as there's the potential for these adverse effects or actual adverse effects, depending on the language of the legislation, PFAS, other emerging contaminants can trigger those orders, those prosecutions, those civil lawsuits.
Okay, well, let's leave it there. Once again, thank you both. Thank you to all our presenters today. Thank you to everyone who registered. Really appreciate that. Thank you to Bureau Veritas and SLR, Terry over at Bureau, and Lindsay and Matt SLR for helping me when I had this idea in my head of doing this day. Appreciate your feedback and help along the way. A reminder to watch your email later today. There'll be instructions of how to download the or to watch the videos. From there, you can see the presentation, get contact information. You can also reach out to me directly if you want to reach out to one of the speakers. I'd be happy to share contact info with you. Reminder, we have our free webinar series returning. We have a couple coming up right away at ESAA.org/webinars. And please register for REMTech about 3 weeks away. Tell everyone you know so they can register as well. It's really cheap. It's like $100. So it's not Banff, but it'll do for this year. We'll be back next year with flying colors and we'll have a great event. So thank you again, everyone. I really appreciate this. Enjoy the rest of your day. Stay safe.
Thank you, Joe.
Thank you. Thanks, guys. Thanks, Jackie. Thanks, Matt.